So this is the design we ended up going for. I'll start off from the middle and branch out in terms of components we ended up utilizing. So the middle section is composed of 4 centering rings, and these are mainly used to position the motor axially throughout the launch vehicle and ensure that any thrust is transmitted vertically relative to the launch vehicle. The bottommost ring, which is the ring you see all the way there on the left, is attached directly to the thrust plate using quarter-ton fasteners. This was selected due to the high stress concentration to that region, due to the fact that the main attachment point is the motor retainer to that thrust plate on the bottom. Furthermore, fin brackets were selected as the main fastening component of the fins to the entire structure on the inside. And this was mainly selected to not have to drill through the wall cutouts into the airframe, which compromises structural integrity, as I mentioned before. And so these fin brackets fasten directly to the inner structure using radial holes that could be easily drilled onto the airframe. Finally, we ended up selecting aluminum standoffs to space the centering rings you see in front of you. And this was mainly selected to ease the assembly process, in which the entire system could be assembled externally to the launch vehicle and then could be inserted into the launch vehicle for final integration. As far as the materials selection is concerned, we ended up selecting aluminum 6061. And this was mainly used due to its low cost, high strength to weight ratio, and ease of manufacturability.
This has been an iterative project. This is our second attempt at designing a system like this. We did make a previous attempt for the 2023 Spaceport America Cup that you can see here. Some key features that are very different about this design from the design that George just discussed are that it did still feature through the wall fins and massive slots that you can see in the airframe right there. The centering rings were also very thin and were not meant to be load bearing at all. They only served to hold the motor casing concentric. And then there were no aluminum spacers, so each ring had to be installed on its own, which made for a very tedious assembly process. And our manufacturing processes were still in development and were not fully fleshed out, so we had some errors there as well. This design was not successful, as you can see here. This was from a test flight we conducted in Florida prior to attending the 2023 Cup. And so we did still attend, but we ended up coming just with an epoxy apt instead, and were then able to just kind of assess this design and move forward to this year. One of the biggest downfalls of our design in 2023 was a lack of mechanical analysis and really understanding the loads that were being applied onto the system prior to actually flying it. So going into this year, our number one priority was to thoroughly understand the loads that were going to be applied and actually conduct rigorous analysis on them. This started by assessing the failure modes and cases of our old design. So some modes that we considered were potential fin flutter, uneven fastener distribution, and just overall failure due to lack of part strength. We did several different analyses on that, but the most important one really is shown here, just a small portion of that design, where you can see a very high stress acting on the structures themselves. So we were able to really narrow it down that our number one issue was just lack of structural integrity in this design. So with this in mind, we were then able to move forward into the analysis of the system that we designed this year.
Yeah, so I'll now discuss some of the key design considerations that went into developing the upgraded motor retention system for this year. So one of the main considerations we had for the design was simulating the loading applied on the fasteners using the system. This was mainly selected due to the high loading applied specifically on the shanks of the fasteners during flight, and that load is directly transmitted into any other components of the assembly. The equation you see in front of you shows the number of fasteners needed to achieve a certain cross-sectional area to maintain, to decrease the overall stress on the fastener and ensure that it is below the ultimate tensile or shear strength of the specific fastener in use. So after conducting the fastener analysis, here are some of the results for different sections of the assembly. So the first column shows the fastener results for the topmost centering rings. The second column shows the radial hole selection for the bottommost ring. And the third column shows the connection between the bottommost ring and the thrust ring. As far as the material selection is concerned, we ended up selecting black oxide steel. This is mainly selected due to its high ultimate tensile strength, in which we could select smaller size fasteners that exhibited relatively high strength and decrease the overall weight of the vehicle. As far as the specific fastener size selected, we ended up selecting 632 fasteners for the topmost centering rings And this was mainly done so because the only main force applied in that section is the inertial loading of the launch vehicle during flight. This is contrary to the bottommost section of the assembly, in which the bottommost ring is connected to the thrust plate, which required larger size fasteners due to the application of most of the thrust into that section of the assembly. Therefore, we ended up selecting 1024 fasteners for the radial holes into the bottommost ring, and quarter 20 fasteners for the connection between the bottommost ring and the thrust plate. And then here are some more properties of the fasteners we selected, such as the cross-sectional area, major diameter, and yield strength. So after determining our fastener analysis, we went on to derive our static loadcase. So that was split into three main forces, the first of which is the thrust force, and that was found by determining the maximum thrust curve with the motor selected, which was an Aerotech M3300 motor. The second major force determined on the structure during flight was the inertial loading, and this is not a real force applied during flight. This is more so a simulation of the dynamic model of the rocket, which could then be translated into a static one that could more easily be simulated. And it was mainly found by determining the maximum acceleration determined during flight using an open rocket simulation of the launch vehicle and then multiplying it by the total mass of the vehicle. The final major force applied during flight is the drag force, and that was split into two main components, the X component, which is applied directly onto the tip of the fin, and the Y component, which is applied directly to the side of the fin. The equation you see in front of you was used to determine the drag for each component, and the variable of main concern was the drag coefficient. As far as the X component of the drag is concerned, we ended up selecting a relatively high drag coefficient in order to ensure that any simulated drag within that component is higher than any drag that can be achieved during flight. As far as the drag component of the second component, which is applied directly to the side of the fin, we went under the assumption that the side of the fin is a flat plate and determined the worst angle of attack achieved during flight, as is shown on the figure on the right. And then we determined the drag coefficient based off of that. After that, we determined the maximum velocity achieved during flight, which is shown in the figure on the left. And that was mainly used to plug in the equation shown before and find the two main components of drag achieved during flight.
Once we had finished deriving all of the values, was figuring out exactly how to apply them onto the structure itself and begin building our FEA model. ANSYS Mechanical was our selected platform in order to do this, and the model that we selected to do was a halved model of the overall system. This allowed us to decrease computational time while still getting a fine mesh and accurate results. To further do this and decrease that computational time, the airframe itself and the off-the-shelf motor retainer were not included in this analysis. This is just our structure. The loads, how the loads were applied, are shown here on the left. The thrust was applied directly into the thrust plate. The inertial loading was distributed throughout the four centering rings in the same way that loads are distributed onto the threads of a fastener. So the top ring bore 38% of the inertial load, the second 27%, third 20%, and the bottom 15%, just to get that distribution throughout that structure. And the drag was applied onto the fin bracket connection in opposing directions, so as to simulate the flow during flight. And then finally, we also applied some bolt pre-tension onto the bottommost fasteners, as that's where the clamping onto the airframe is occurring. The supports of the system are shown on the right-hand side case here. Since this was a static study, we did need to have one fixed support, and we opted to use the lip of the thrust plate's interaction onto the airframe as our fixed support, so that would be taken to be not moving. All other supports were taken as frictionless. This included the interaction between the fin brackets onto what would be the airframe, also their location vertical along the airframe, and the section faces of the halved model. In order to get our results, we performed iterative analyses. So we started with analysis of just fully solid centering rings, which was way too heavy and never our intention of a final design. But we wanted to really get a look at how this load case acted upon this structure and then be able to build our design around that. And so this is our very initial simulation where we were able to identify the bottommost centering ring and the thrust plate as the points of highest loading, so that we could then design weight optimization cutouts around those high stresses. The second and third iteration iterations, particularly on these points of highest loading, are shown here. In our second iteration, we went for a large amount of mass removal, and then we actually saw ourselves going past yield again in locations. And so in these instances then, we were able to once again assess where those points of highest loading were, and then add material just specifically back to those locations to continue to optimize both the strength and the weight in tandem. Our third iteration is shown here with some of our more acceptable results. And then on this slide here, you can see the final iteration of the whole model and our results for that. Something to note real quick here, you'll notice on the table here, there's some very high loads listed as max. These are acting on the fasteners, and as George already discussed, we did our fastener analysis by hand, and so these loads are just inaccurate loads, not actually acting on the model, just for ANSYS. The mesh wasn't fine enough on the fasteners, and so that was giving us some faulty results, but we did those calculations by hand, so we just didn't consider those results. We're only considering the results on the structure itself. The yield strength of aluminum 6061 is 35 KSI. Our maximum simulated von Mises stress on the entire system was 26.3 KSI, with a maximum simulated von Mises strain of 0.0026. Our target factor of safety was 1.1. This was taken from NASA Standard 5012B, which is an aerospace standard for the analysis of metallic components in rocket parts. And this gave us a margin of safety of positive 0.21, which we deemed to be an acceptable value. The final mass of the system overall was 95.22 ounces, and just for reference, this is half the weight of the epoxy act that we brought to competition last year. So we were able to significantly decrease this weight, and so our rocket this year is significantly larger than our rocket was last year, but is still able to hit the altitudes that we want because our oscillation has decreased in weight so much. So with the design finalized, we'll now move into talking a bit about our manufacturing iteration and tests of this system. Our manufacturing processes were fully automated this year, which was an upgrade from last year as well. Everything was done either with abrasive water jet cutting or with CNC machining. The centering rings, their overall shape and the cutouts were all cut from flat plate on an abrasive water jet cutter. Any pocketing that needed to be done on them was done with a 3-axis CNC mill, and then the radial holes were done on a 4th-axis rotary table, utilizing a custom jig to hold the part. And this was a big upgrade from last year. We had been doing this process manually, and it was very time-consuming and not very accurate, so this is a big improvement for us. Our fin brackets are entirely machined on a 3-axis CNC mill through a series of operations that allows us to just batch out one operation at a time. And doing this, we're actually able to make all of these parts in the span of only a few days. All of our CNC work is done in-house at the University of Florida, and all of the programming and the operation of the machines was done entirely by the two of us, myself or George.
So after completing the manufacturing process, we moved on to assembly, in which all the components were successfully assembled and inserted into the launch vehicle. One thing to note is the bolt preload, which is the force exerted onto the shank of the fastener as it's being torqued down further for proper clamping force, was inserted into the FEA model. A minimum value for that preload was selected due to the model sensitivity for increase in bolt pretension, in which the bottommost ring would experience failure if the bolt pretension was too high. When that bolt pretension was then converted to a torque using the nut factor, which is a material or a variable correlated material of the fastener and nut selected, as well as the major diameter of the fastener, a low torque was achieved, which was not enough to withstand any vibrational forces from loosening that connection between the bottommost ring and the breastplate. In order to combat this, we ended up selecting aluminum spacers to be inserted between the two plates, which can be shown in this picture. And after finalizing that, we ended up going with a test flight to test the final assembly. So during the test flight, the picture on the left shows the model after the flight, and as can be seen, the rings do not experience any major failure due to any flight forces, which is pretty relieving and meant that we were somewhat on the right track. Additionally, the fin brackets were able to withstand the loading from the drag during flight and were able to successfully clamp onto the fins. So after conducting our test flight, we conducted one final simulation to see the effects of adding aluminum spacers in final assembly. And as can be seen in the picture on the right, the overall stress in the bottom region of the assembly was vastly decreased, in which the stress was mainly absorbed by the aluminum spacers added. Now this is one aspect of the design that could be further improved, in which the bottommost ring and thrust plate could be further optimized for mass reduction and we could rely on the aluminum spacers for stress absorption. Additionally, this design is modular and has the ability to be designed around various design criteria. And as far as manufacturing is concerned, further developed manufacturing processes could be implemented in order to reduce manufacturing times and increase overall part quality. As far as the validity of the FEA model, further tests could be implemented that include implementing strain gauges onto each component and simulate loading on them in order to develop loading patterns that validate our predictions. And these are some of the components that we look forward to work more on in future years of development of the loading engine. Thank you.
Thank you, and we're going to
This might not be a good question. What software do you use to do all your like stress analysis?
ANSYS.
Okay.
ANSYS PM.
Okay.
So those centering rings are directly touching casing, and motor casing gets pretty hot after it's fired. Do you have any worries about losing your temper or aluminum? Like, do you have like a process of like, swapping this out after X amount of flights?
That's not something that we've considered yet. In our old design, that was a concern we had in some of the previous iterations, that we might see some like expansion or have to worry about the thermal effects more. But we haven't seen in our test flights, really it's our second test flight now on the system, we haven't seen any negative effects from that. So currently there's no mitigation in place for that.
Did you experience any loosening of your fasteners after split?
No issues.
We did experience a little bit of corrosion, but we did land in water because we are in Florida. We landed in a swamp, so we had to replace all our fasteners. But other than that, no.
This is another question about so like how did you guys end up using, like what kind of tube did you end up using when that did you end up using a tube at all around the centering rings? Or
Purely intersects motor case.
So this right here, you can see this is the inside of the airframe that directly interfaces onto those centering rings, and then the motor casing just slides right in. So there's no like external motor tube at all.
Oh, okay. Okay. And like that doesn't affect driving or anything like that? Do you still like just use a coupler to connect that to the next one?
Yes, this is see here, and then actually like all the way back to the beginning. See our whole block. This is the whole entire app section. That's all just mounted in here, and it just comes up, rivets in as normal.
Okay, cool.
Have you guys seen any similar designs to what you guys have on teams around here or anywhere else?
We have seen some different variations of this. A lot of the ones that we saw prior to designing ours were very bulky, which is why a big consideration for us was like cutouts and weight optimization, because we wanted to avoid that. We were going, not just for modularity, but also for a decreased mass. And so, in particular, in that respect, I feel like that's something that sets our design apart, along with just the number of centering rings to distribute that loading. I've seen designs like this as well, where there's just less going on really in it. And so, in terms of loading, what their design criteria is, but for us in particular, sure, distributing the load throughout the number of centering rings. once again, so that the center rings we did have could be lighter.
Software run on this in flight?
So we use a teensy.
Okay.
A BMP 3D.
So for your CFD to get drag coefficients, you find there was looks like you just use constant drag coefficients for the rocket flaps. You find there was significant variation in flight angle and Mach number.
No for Mach number, and we got these cookies drag from our internal testing about CFD.
Oh.
Yeah, so there were like slight variations of coefficient drag on like it is a function of flap angle, but not by that much. So we just have to comment for it. Yeah.
When you were showing the camera filter, you said it pretty much dies at apogee.
Yeah.
Is that because of a limitation potentially in the Kalman filter, or
Yeah.
what's?
Like it's a work in progress to get it past apogee, but it just hasn't been a single point of it. Like differences. Yeah.
Is there a maximum like flap angle that it's limited to?
Yeah. Sure. We try not to have it go all the way out. Like that.
Yeah. And is that because like due to mechanical like stress on it, like you don't want to?
Yeah, it just our motor not that good, so it kind of stalls sometimes. And if it comes out this far, there's so much force on it, it can be hard to control it. Yeah.
Is that entire coupler just the integrated module itself?
Yes. So there's a linear actuator up here, the disc here. Linear actuator moves the disc up and down. So when it goes up, the flaps go in. When it goes down, the flaps go out because there's 4 fluid rods on the disc connected to the flaps. And then it stops up here, and then the rest is piece.
So it looks like the drug would be just above it, or making or checking if they're going to be the flaps are going to be closed before the deployment occurs.
It should be. It has been in the past, and there's been no noticeable effect. But yeah, it's supposed to go back to average.
How's that built into the MPC? Like if it's just if where you're at gives you an estimated keep the current with one angle. How do you build it? Right.
Velocity 0. Determinants for average. Yeah.
For these sensor noise values, were those just taken from the data sheet, or is that something you characterize yourself with the physical components you're using?
Like how we determine the noise?
Yeah, like how you determine like the amplitude and like the noise.
That's really just guessing check. Trying to match, looking at multiple flights, multiple parameters from the flights, and just manually and matching it.
Well, for the MPC, do you find that like some of the base photo method is not just which is what needs more advanced than RK4?
So we don't like our hardware is integrated, we put in the integration vibration. So like it in the code it literally just goes so we can integrate it and just solve this.
It's not just 5 minutes.
Thank you.
Sound off.
Silent. So that is the plan. I what was the Yeah. Good job.
I guess so. Yeah. We're just gonna sit by and see it basically.
Yeah, let's get some pictures. In here. Yes. Okay, so you say here? Alright, that's on the truck lighter. Connor, I think you got 3. I don't think you need me.
Correct.
I will.
They ended up coming in all late.
Yeah, I'm gonna
That's fine.
send this down, guys. But I'm here if you need me.
Thank you.
But. That's a question. You guys are sitting what? We were just here for the previous one. We can move back. We should. We're not gonna. Yeah, so that's the value of the okay.
They can probably hear us, so we can't say silly and stuff. But we can record it. How we put this to make fun of Gavin. Yeah, my mom took a photo of me and sent it to me. Off the camera. Yeah. Oh yeah, you talked about that. Yeah. You said this looks opposite to the left. Turn around. Yeah. Yeah.
We'll talk about that.
Do you think she actually saw your
Picture of it. Yes, I think
But
that's what
the
they're called.
camera wasn't moving that way.
No, it's really white.
Really?
Yes, outside on the ground in front of the earth, underneath the tripod. Thank you.
I'm
180.
That is not 180. That's maybe.
That's fine.
Oh, I think 10. Yeah, but that is.
So I'll try to
Phoenix Charlie.
No, I was about to say the exact same thing. I was going to say that's not 180, that's 180. And then I processed.
That's not winning. That's not winning.
Wow.
You're truly a genius.
I know, I know.
Right. You don't want.
Caleb, just take him pants. Caleb,
Makes us feel better now.
Excellent.
I'll just back straight down for the
Oh, you got it. Got
It's not. Yes. Not gonna be.
That's actually your tripod.
I stopped in to get there. Here's going to be here with you. Yeah.
That's slightly too weird. That's really like this. Well,
Alright, hello everyone. My name is Gavin House. I'm the president of the University of Minnesota Rocket Team.
And my name is Caleb Vogel. I am the recovery sub-team lead for the university.
So we will be presenting our knotless recovery harness and parachute for weight reduction and strength. Well, off to a great start.
So our entire recovery system is completely designed and manufactured in-house. This is a brief overview of our recovery system. It is a standard dual bay, dual deploy design with the drogue parachute located in the booster tube and the main parachute located in the upper body. A couple things to note: we use black powder ejection charges to separate our rocket, and employ the use of deployment bags to ensure a more reliable recovery. And the length of each recovery harness is about 5 times the length of our body tube, of our rocket. This year, our main parachute is an extended strip design based off of the US military's T-10 parachute. It is about 20 feet in diameter with 12 gores. It has a coefficient of drag of about 0.65, and the design was chosen due to its very stable descent to ensure a more reliable recovery. The drogue parachute is a disc gap band design based off of the parachute used by NASA for their Viking lander. We have used this design on many previous SA Cup rockets and are very confident in its reliability. This year, the parachute is about 5.5 feet in diameter with 9 gores and a slightly lower coefficient of drag of about 0.45. Both for the drogue and the main, those coefficient of drags were found experimentally using subscale parachutes on test rockets. And again, for both the main and the drogue parachute, all of their parachute geometry was taken from the Kaneki parachute manual. Like I said before, our entire parachute is manufactured in-house by our recovery sub-team. We make our parachutes out of nylon, which is a very lightweight and strong material. We cut the gores out of 1.1 ounce ripstop nylon, and this year we dyed some of the gores to make our parachutes visually distinct and to increase their visibility on descent and during recovery. We connect each gore together using a straight stitch in size E nylon thread and reinforce each of those seams with 500-pound nylon tape. The nylon tape was also used to create our attachment points for our suspension lines, which connect our parachute to our recovery harness.
But before we can talk about what's new about our recovery harness this year, we have to talk about what our old recovery harness looked like. So this is what a recovery harness would have looked like in 2022 here at IREC. So it starts off with a steel U-bolt connected to our fiberglass bulkhead. This then connects to a steel quick link, which it has been tied onto by tubular Kevlar rope. The tubular Kevlar is tied into a scaffolding knot that can then be slid onto the quick link and tightened during integration for quick assembly. This then connects to 2 quick links around a swivel, which runs up to our high-strength Kevlar suspension. So if you look at this design, there's a number of metal components, making it rather heavy. The main parachute plus main recovery harness comes in at nearly 15 pounds, whereas our new recovery harness has moved to remove these metal components and knots. So this starts at, again, a steel U-bolt into our fiberglass bulkhead, then a soft shackle, which again can be linked on quickly during integration. This is linked through a Dyneema shock cord, which is spliced into an eye that's slid onto the soft shackle. On another soft shackle is a deployment bag. This is an SRAD deployment bag that's made by the team. To another 2 soft shackles housing our swivel up to Vectran suspension.
So, like I said, one of the new things we've added in recent years is the implementation of deployment bags. Deployment bags are typically made out of some sort of fire-resistant material and have a compartment for your parachute canopy and then a section for suspension lines around it. The main purpose of deployment bags is to protect your parachute from the hot gases of ejection turges. Similar to that of a chute protector, we use deployment bags instead of chute protectors because deployment bags allow us to sequence our deployment, which helps to reduce opening forces and provides a more reliable recovery. This year, we decided to make our own custom deployment bags out of Nomex fabric to create a better fit for both our parachute and in the body tube itself. Most deployment bags use some sort of pilot chute to pull the parachute out of the bag, but our design uses the force of ejection and the elongation of our shock cord to pull the parachute out of its bag. Another new aspect of our recovery system is our implementation of soft shackles as an alternative to quick links. Our soft shackles are made out of Dyneema and consists of an eyelet wrapped around its tail that is then stopped by a stopper, preventing the soft shackle from becoming undone as seen in the photo. The soft shackles we use this year have a very similar braking strength to quick links we have used in the past, but are nearly half a pound lighter, and then with a dozen or so connection points across our entire rocket, those weight savings add up rather quickly.
So we mentioned a number of different materials throughout the new harness as well as the old harness. So we'll go into some of the decision-making process that went into those. So using our 1/8-inch suspension lines as a benchmark, we evaluated high-strength Kevlar line, Vectran, and Dyneema. The high-strength Kevlar line is aramid fiber at 21 cents per foot. It has a 1,800 pound breaking force. It's heat resistant and abrasion resistant, but rather difficult to splice due to it being a really fibrous rope. Then there's Vectran, which is a liquid crystal polymer. At 67 cents per foot, it's a rather pricey fiber, but it's heat resistant, easy to splice, and it comes with a urethane coating for abrasion resistance. Also making it rather slippery, so the lines won't be tangled during deployment from our deployment decks. Dyneema is an ultra-high molecular weight polyethylene. At 30 cents per foot, it's sort of the middle ground with a 2,100 pound breaking force. It is the strongest of the three. It's easy to splice, but it's susceptible to heat and abrasion. So looking at these three fibers, we have some pros and cons of both, with Dyneema being poor against heat and abrasion, which can be expected from a black powder ejection, as well as rubbing on the rocket and the edges of our body tubes. Vectran's rather expensive, and Kevlar is cheap, but it's unable to be spliced. Taking that into account, we can actually see that the high-strength Kevlar is the lowest strength of those three once it needs to be tied into knots on our nylon tape. So to find that result, we used a material testing setup that consisted of 2 steel pins through a test section. The knot that we were testing would be tied at the top and bottom, and it would be pulled into tension. This is a test on one of the Vectran lines. And it would fail rather explosively. But something to note in that video is that Vectran line was spliced at both ends, and it broke in the center of the rope rather than at one of the knots where the where the stress would have concentrated. So that's a good sign in our test. And then we can go and look at the data. We evaluated surgeon's knot, a clinch knot, a figure 8 knot, a bowline knot, and a scaffolding knot, all on that 1/8-inch material, as well as 2 knotless techniques, a Brummel eye splice and a technique we're calling a finger trap splice. The knots, the strongest of the knots, had a tested strength versus manufacturing spec of 29.8%, meaning that the knot was breaking at about 30% of the rated manufacturer strength. Whereas our knotless techniques were breaking at 100% of the rated manufacturer strength, meaning that we were no longer having stress concentrating in those knots. Taking that data into consideration for our old harness and all of those knots using that experimental value, for our scaffolding knots, we can see that we actually have a 2,144 pound break force on our shock cord versus the 7,200 we expected off the manufacturer's spec. With shock force calculations of 1,500 pounds, we were concerningly close to the shock force that we could expect for our breaking strength.
So then, through all of our material testing stuff, the main design improvement we were looking at is trying to eliminate those stress concentrations of knot. In the knots, that's just primarily done through splicing. The basic concept of splicing is taking the tail end of the rope and veering it back into the rope itself. And then as a load is applied to the rope, the outer section will go and constrict around that intersection of rope, providing a very firm and secure hold. For the Dremel eye splice, in order to prevent the splice from coming undone, when no load is applied, the tail end was weaved back through before it was buried, as seen in that photo. And then another thing to note is that before the tail end is completely buried, we go and taper the end of the rope to go and help reduce stress concentrations as it transitions. All right. Very similar to the Dremel splice, the finger trap splice also has that tail end buried in. But instead of weaving the tail end back and forth through, we added a couple of there's a couple of stitches there to keep that inner rope in place. And then again, the tail end was cut at a 45-degree angle to help reduce those stress concentrations in the splice. Taking into account all of our material testing and research and design constraints for our project, we ended up going with 1/4-inch Dyneema compared to the 1/2-inch tubular Kevlar we were using before. This was primarily due to Dyneema's ability to be spliced. We chose Dyneema over Vectran due to Dyneema's higher strength and lower cost. We went with the Dremel I-splice as it is much easier to do on thicker diameters than the finger trap splice. And then to counteract some of Dyneema's more negative qualities, specifically for the Nomex sleeve around the section of shockboard closest to the ejection charge, and then added extra zippering protection up by the rim of the body tube where abrasion might happen. For the suspension lines, we went with 1/8-inch Vectran compared to the high-strength Kevlar line we were using before, which allowed us to greatly increase the overall strength of our suspension lines, primarily due to the implementation of the finger trap splice, which removed all of the stress concentrations from the knots. The finger trap splice also allowed us to make each of our suspension lines the exact same length to reduce uneven loading on the parachute itself. The urethane coating on Vectran also helps to reduce the chance of tangling of our suspension lines and makes a much smoother deployment from the deployment bags.
So looking at our new harness in terms of minimum braking force, our suspension lines have a 19,200 pound braking force. The braking force of the soft shackle is 10,000 pounds. The shock cord is 7,700 pounds. The swivel is 6,000 pounds, and the minimum braking force of a component of our SRAD recovery harness is our McMaster car idle at 5,375 pounds. So looking at this versus the old harness, we have gone from 14 pounds to 8.5 pounds, and we've had a minimum component strength increase from 2,000 to 5,000 pounds. That's at 60% of the weight of the former harness, we have 4 times the strength. With 0 knots, the harness has no chance of having a poorly tied knot, increasing stress in that location, and has relatively the same manufacturing time. So the key takeaways from this then are that small and easy changes to our manufacturing and materials can have great impacts on our weight and strength. This then can be taken and applied to more optimized flights like a high altitude rocket, or weight savings on an SA Cup rocket carrying multiple payloads or avionics systems, as well as future work can be investigation into shock forces in the harness, and then using that better understanding of those shock forces to investigate cutting down on those large safety factors. Thank you. Any questions?
So overall, how much more labor intensive is the process that you're using now versus knots?
It's not too much more labor intensive. There is a slight learning curve to it, but once you get that down, it's pretty quick to splice a section of shock cord or something.
And I would say the learning curve doesn't look that much different than being able to tie a good, consistent knot at equal length. Especially for the finger trap, it's a very easy technique, and because we want those to all be the same thing, you can mark out the distance, slide it through that exact distance, and sew it to that distance, and get your perfect measurement.
How many people on your team have you actually gotten to learn that process?
So
is it a one-man show, or is it
no. So there's probably about 5 or 6 people on our team that have done the Bremo splice, and then probably 3 or 4 that have done the finger trap splice.
With the Dyneema,
Have you taken into account like or have done any testing on like abrasiveness or like sheathing on body tubes at all?
So we haven't tested that abrasive, the effects of abrasion on the Dyneema. To counteract that, we fly a small section of pool noodle on our Dyneema that's wrapped in Nomex at that distance and then zip tie it on to ensure that there's kind of a nice surface for the Dyneema to rest against.
We also go and we'll pile down any towards marks or any sort of blemishes on any eyeballs or evils that we have to ensure there's nothing for them to like rub against. Yes.
How does sewing lines reduce the manufacturer rated strength of your lines?
On the fingertip splice?
Just generally, and specifically that.
The sewing isn't reducing the strength.
Okay.
It's the knotting of the lines.
I see.
Is your question getting at the fact that most teams are using just a sewn recovery harness, or the loop is you look like a 1-inch tubular nylon sewn back on itself? Do you have any?
Yeah,
thoughts on
so
comparing that to this.
in comparison to that, we usually fly pretty heavy rockets. The rocket this year is 145 pounds. So we usually need kind of a stronger material for those shoots, and also doing this allows us to have a rather long suspension lines all be the same length with that technique, so we have no concern about that. And then we can tie them onto the swivel all with that like same length. And then we also do this then to allow us to interchange lines in case anything comes up during transporting the rocket to here from Minnesota, or during ejection charge testing of the rocket if a line gets damaged. It's way easier to switch that out than have to resew a line or shoe.
With like the stitching of the suspension lines using the finger trap, is it possible with the? I'm not really familiar with the Vectron. Can you like run or slice the those suspension lines? It's like then you don't have any stitches.
Yes, you can Dremel splice the vectran and stuff. It's just a lot harder to get those the same length because of that action of weaving the tail back and forth to lock the splice in.
Yeah. There's a different method like I found online where basically you can lock it in and you can like highlight or draw texture on and then you draw the 2 points up so you get the exact length. We did that, but it is quite like labor intensive.
Yeah,
stitching.
The finger trap is like just the two of us were able to get all of our suspension lines done for both parachutes in a couple of hours with the finger trap method, because it really is just going in with the line and then stitching. It is rather short.
Do you guys have a process for determining a group of your knots and your cores and stuff like that to be for flat? Do you guys just fabricate your different components and then go right straight into flat? Do you guys have like maybe a stress test, minimum stress test at least put on it?
We did test samples of all of these different connection methods. And then for like actual flight stuff, we use completely new vectran and Dyneema. And then go and we'll visually inspect all of our suspension lines and shop or like.
You go through the minimum test of stress or
No, we don't.
make sure you don't like record test. Yeah.
No, we do not. Yes.
You also mentioned that you're worried about the Dyneema having heat from the flat tire charges. What did you do against that? Because you mentioned abrasion, but not.
Yes, so for the shock cord, we go in probably a good 15 feet. The 15 feet closest to our ejection charges is wrapped in a Nomex sleeve, and Nomex is a fire resistant material.
And that material is included in the weight of the recovery harness when we're talking about the weight range. So,
yes.
Have you just said that you use new lines for new launches? Have you looked at how over time do the line sets become weaker and weaker, or are you able to like use it and then use it again and again, or
So for specifically for the SA cup rocket, we do a completely new set of stuff. But for test rockets and stuff, we have flown it multiple times, and then but we have no at least with our tubular Kevlar we used to use, we had an old test rocket where that line actually broke after a number of flights.
Yeah, we do find too that the conditions in Spaceport, like the dust and stuff, can pretty significantly degrade lines. So we try to avoid reusing them if possible.
How about with ambient temperature?
And yeah, I'm not 100% sure about ambient temperature, but it's within thinking of the lines. But also once they're stressed to some degree, we like to just use new ones.
Why did you guys choose a discount band for your drone?
So that's a design we've used many times in the past, and very familiar with it. But that design also is stable on descent, and also has a slightly lower coefficient of drag, which makes our parachute slightly bigger, which makes the manufacturing of it much easier compared to if you had something with a high coefficient of drag. Now we're getting to like a 2-foot chute instead of a 5-foot chute.
You said you used the US military sort of dome style parachute for your main. Obviously, like your aim here was like really reduce weight across the system. Is there a reason like you didn't, or are there benefits to that parachute, or reasons you didn't go with the more, like those parachutes like toroidal style ones, which have like coefficient of like 2, or greater? Is there a specific benefit you get to those military dome style parachutes?
So we take all of our parachute geometry and stuff and how to calculate the size of the door from the connected parachute manual. So we're somewhat limited into the designs that they have without a significant amount of research into getting the correct geometry and stuff. And of those ones, the extended strict design does have a relatively high coefficient of drag compared to other ones that aren't, much more difficult to manufacture.
How did you estimate your opening shock forces for your HUs?
So that's a calculation that we took from the ConnectView manual. It involves the dynamic pressure on the chute, the coefficient of drag, which we use our experimental, and then the nominal area, and then a shock reduction factor and a safety factor into those. Those are just calculated with some worst case shock reduction of 1. So real shocks are probably going to be less because on our main, at least, there's not the parachute is sized for the size of the payload.
We have the custom made component back. Where did you stow the suspension lines? Was it like actually?
Yeah. So the suspension lines are there's main almost cylinder section that the canopy is stored in, and then around that there are some elastic bands that we go and put the suspension lines in, and then there's another Nomex sleeve that goes around to add extra protection.
Yeah. Okay. Thank you. Interested in looking at them too? We have samples. We could show them at our table after the introduction.
124.
Oh, 124.
We haven't gotten the judgment yet. I'll say
Yeah. Oh, yeah.
That's a contract there.
Yeah. With the Podium presentation, like this
Why would you use it?
even though
I think that was just close us down at the year.
Okay. So, yeah. Okay.
And not, they chase you down the phone and said, you have to talk about this.
Yeah.
Yeah, thank you.
Just to make sure that so we can find the lords.
Mike, are you a judge for the UT SAT? How many other people are with you?
There should be one more judge coming.
Okay, awesome.
Okay.
Appointments for those? When I come into the finance level block, you have your top to the last. All appointments for out 50, and then go to the judges.
So sorry, you said 20 minutes to present like the spot. That's one.
Yeah. 20 full.
Okay. Okay. Nice.
Finish your last sentence.
Okay.
Go 55. Then after that, final over, all four, do this. Finish your last answer.
Yeah. Okay, cool. Sweet.
We'll start exactly on my clock.
You close the door. Okay.
Are you also a judge? Oh yes.
Yeah.
Oh. Am I here? You have a better day? Yes. Okay, if he doesn't show up, I'll make sure. But you're not and then I see Steve come in. Does people don't show up, I'll have and give that's their color done. What?
I said
T minus 10 seconds.
10 seconds. All right. Okay. And we're from the Aeronauts and Rocket Club at the University of Texas in San Antonio, giving a presentation to the 2024 IRAC competition. Our podium presentation is about using laser spectroscopy to measure and estimate chamber temperature of SRAD solid propellants. So a quick overview of the presentation. We're basically going to have a quick introduction, the purpose of the scope of what we're trying to do here, the theory of laser spectroscopy for those of you who may be unfamiliar with it, how we set up our experiment, and the procedure that we follow in order to gather our data. Then we'll talk about the lengthy data processing experience and discuss the results and conclusion of what we've done, and also any future works that might spring out of the work that we've completed, as well as acknowledgements and announcements at the very end. So, quick introduction. This is UTSA's first year of doing student research in developed propellant.
And we're working very closely with a lot of the graduate students in the Laser Spectroscopy and Chemical Propulsion Laboratory, otherwise known as the LSCPM. There's a lot of graduate students there who are very interested in what we're doing at ARC and wanted to apply a lot of their laser spectroscopy research to some of the propellants that we've developed. So there are aspects of propellant combustion that are still unknown. From a mechanical background standpoint, like it's reliable enough that we can use it on a very regular basis. It's known enough that we can use it reliably. However, especially on the atomic level, there are still some muddy areas, particularly what happens inside the chamber, right? We don't exactly have the ability to put high strength cameras in there or anything like that. So there's some parts that are just not quite characterized. The only reliable data we have, especially at the hobby level, is burn time, thrust, chamber pressure, and sometimes with smaller motors, having pressure chamber reports, and that can kind of affect the performance of your motor by increasing your volume. And something we want to kind of it's not desired. Measurement of flame temperature, especially with commercially available equipment that anyone can go buy, is nearly impossible. You can't measure the inside of a chamber temperature of a motor. It's even with like NASA grade thermocouples, it's pretty hard. So what we'd like to do instead is utilize wavelength modulation spectroscopy to measure HCl concentrations that come out of the exhaust flame of our APCP motors and use that absorption data to basically process it into temperature data. And we're going to use a method called two-line thermometry to determine the exit flame temperature. And overall, what we're trying to do here, this is a first step in determining is it viable to use laser spectroscopy on solid propellant combustion to determine characteristics of that. So real quick, is anybody familiar with laser spectroscopy? Okay, cool. So I might be able to get away with, saying some crazy things. So very close. So in a nutshell, basically, you have an intensity of light at a specific wavelength, and if it passes through a medium, that medium can absorb that wavelength or that intensity at specific wavelengths, and that is a measurable ratio that is described by something called the Beer-Lambert law. The most exciting part of that law is the beer in it. Otherwise, it's a very complicated model. But in a nutshell, it is a function of mole fraction of the medium, the pressure of the medium, path length, temperature, and it's also wavelength dependent on whatever the wavelength of the intensity of the light going through. A good example of this is how gamma radiation gets absorbed by the ozone layer in our atmosphere to where it protects us from the harmful radiation of the sun. Right? It's basically just like that. However, we can utilize it to our benefit with solid propulsion measurements. Hydrochloric gas, HCl, is a product of all APCP-related propulsion systems. And it just so happens to have absorption transitions in the 37 nanometer range, which happens to be the frequency of the lasers that we had work in our lab at the LSCPM. So what we're going to do is we're going to take absorption data that we measure from our exit flame, and we're going to process it into temperature of the exit flame.
And the data in the graphs here that we'll be comparing later on, they're all taken from the Spectroplot database. These are all fully researched, like these are confirmed, and they give us a good baseline that we know, okay, this is for sure where HCl should be.
Sweet. Quick overview of two-line thermometry. I'll be very quick. This is a math class. Basically, two things you need. The one thing you need for two-line thermometry is two transitions, one of which does not vary with temperature, and one that varies rapidly with temperature. So here we can see, as Grace said, this is the HiTrend database or Spectroplot database of HCl transitions around the 37 nanometer wavelength area. We have one here that does not vary with temperature at all. This one varies greatly. What we do is we basically use this one as a control and this one as a temperature dependent, and we can find a ratio that becomes basically a function of temperature. And if we find experimental data of these transitions, we can apply that function to it to get a temperature out. Does that make sense? Maybe, kind of, sort of? Sweet, thanks. So this is a quick overview of our experimental setup. Basically what we have is a laser that shoots a beam through our exhaust gas and then back into a detector. The purpose of the detector is basically to detect drops in the intensity of wavelength, intensity of the light at a specific wavelength that is absorbed by the HCl in the exit flame. This is a picture of the hardware that we use. We have a small test stand motor here. We've used this for characterizing 54s, 38s, things like that. It's called Tetra. She's very beautiful. And then she's centered in between two raised platforms. Those two raised platforms are basically Thorlabs platforms that are specifically used for laser mounting hardware. So we have a laser mounted here, a series of 5 mirrors that bounce the beams around, and then back into the sector in the back. All of this is placed inside of a fume hood for safety reasons, of course.
And one of the issues that came to us is we have a shield. We'll explain more later, but we did use a shield to protect most of our hardware from the extreme temperatures from the flame. And you may be able to see this one hole right here, but it does also feature.
Cool. This is a top-down view, basically kind of demonstrating the path that the beam takes through our system. You'll notice that the beam goes across the flame and then back the same way it came. The reason we do that is to increase our path length. Path length is directly related, directly proportional to the absorbance. When we increase the absorbance by bouncing it across and doubling our path length, we reduce the sensitivity of that data. So basically, if we just have one going across, any small variations in HCl concentration would lead to more sensitive data. The motor that we ended up testing for this was a small 38 millimeter F-class motor. It ran at a very, very low pressure compared to what you might be used to, around 60 psi. And the reason for that is because we're doing this experiment in a fume hood, in a lab, in a building. We want to be very safe in the event of something going wrong. We want it to be as least wrong as possible, right? That will lead to some issues later on, and we'll talk about that. But the motor does perform very interestingly. Quick rundown of our procedure. Basically what we're going to do before we start is take background measurements and etalon laser measurements. The background measurements are something that we can use later for filtering out noise in our measurements. And then the etalon is to basically change the domain from a time-based to a wave number base. We'll go into what that is later. We installed the igniter in our motor, which at first was E-matches. However, we changed to nichrome when we ran out of those. We start logging the pressure data. All right, we're good. Close the fume hood, ignite the motor. About 4 to 5 second burn time. It's pretty long for, but it's understandable with the motor with that low chamber pressure. Once the motor reaches steady state and stops chuffing, we start the laser scan. It takes 20 sets, or what we call buffers, of data over the course of 1 second. And then after burnout, we save all the data, reload the motor, and repeat. So we have our theory, we have our experimental setup, we have our procedure, we're ready to light the motor. Cool, yeah. Yeah, you'll notice there was a bit of chuff in there, and we'll go over what that means for our data here in a second. Sweet, there.
Alright, so now we have our measurements. What do we do with it? Unlike a lot of sensors, spectroscopy is a lot more nuanced to interpret, so we have to go through a lot of steps. First, overview. We have a photodetector that outputs a voltage according to the photon intensity. We have the raw data right here, and you can see it right straight from the picoscope. That voltage is put into a function generator in a picoscope to convert to a mallet function, which we can then write a script to fit and interpret. This looks simple, however, this is actually not something that we can interpret with the Beer-Lambert law, because as you may know, if you're familiar with it, it is dependent on wavelength. So we cannot interpret this data, which is with respect to time. Okay? So the Beer-Lambert law is integrated and rearranged. We have a very quick derivation of it right here. We have the full derivation in a support slide if you're really interested, but like Ethan said, this isn't a math class, so I'm not going to make you sit there and do all of it. Our measured data is aligned with the background scan to remove noise through low pass filtering and time averaging the scan. This is important because there's gaps throughout the entire path length, which is why we need to take the background scan to make sure that we are only looking at HCl. It's also important because the raw data is going to have a lot of noise in between the transitions. I think I have some more graphs and support slides, but that wavelength is not what you want. We know that HCl is only absorbed on these two wavelengths. So the rest of it is just faulty, it's error, it's not usable data. The N1 data and the free spectral range shape the domain to wavelength number. We said we can only interpret data that's in with respect to wavelength, not time. So we have to ship the data. I have a thorough explanation of what an etalon is and does in this report. Then we use a nonlinear void complaint estimation to fit the data to a void profile and calculate the area. A void profile is basically just kind of like a distribution, similar to like an Gaussian distribution, except it takes into account the effect of temperature on, the light speed, which it's kind of hard to see, but there's very slight differences, right? But this is our graph. Take into that account. We then will take the area of the transitions void profiles, and we use that for the two-line thermometry Hayden was talking about earlier. Equation might look familiar. We have areas that correlate to the ratio of the line strengths, which are dependent on temperature. By using this equation, by plugging in, we can find the line strength, we can find the area of the void profiles, we can then find the temperature. We compare the ratios, which, as I explained, because one does not vary with temperature, we know that this is a pretty good control group. And then after we find the temperature, we can go back to the original Beer-Lambert equation, integrate it, and find concentration, which the simplified version is. Sorry. Results in discussion. So the initial observance data does line up with our Spectroscopy database. Again, it's kind of hard to see from here, but this line, that is our data. We can see that because if we have our control group right here and our variable transition here, we know, okay, we're looking at the right transitions, we're finding it's picking up the right gas, we're good. However, we did run the code. Our initial temperature data came out to somewhere between 1,000 and 1,200 degrees Kelvin, just depending on our buffer, which is significantly lower than our NASA CEA simulation, which put us about 2,600. So it was like a 47% off, but we do have a couple pretty good ideas of what might be. So there's obviously two outcomes. Either data is wrong or it's right, which seems pretty obvious, but that has a pretty big impact on what the next steps are. So first, we have to confirm that, which is going to be our future work. We need to find different programs to confirm the simulated results, like ProPAP and CanCI, just to make sure, okay, it's not NASA CEA, that's like inaccurately simulating our propellant. We can make sure, okay, we're not making it, or maybe NASA CEA wasn't giving us an accurate simulation. We need to repeat the experiment in a larger area to increase simulation, which we will go to the next slide about why that has such a huge impact on what the results may be. And then possibly using an additional sensor to confirm the concentration data, determine if the temperature reading is correct, concentration and temperature in our supervisor version of the Beer-Lambert law. Concentration isn't dependent, or they're not dependent on each other. So they're using that, if we know what the concentration is, then we can test what our code gives us, and we're like, okay, if this sensor gives us 10%, but our code is giving us 15%, then we know, okay, this temperature is not right, we need to go back. The first thing that is probably most likely is just the HCl recirculation, which increases the concentration by the predicted temperature. I have this nice little diagram here that you can see as the gas spits out. It will flood the fume hood because it is a small area. Small contained area, even with the ventilation, like it's a lot of gas, it's filled up. And because the laser or the detector detects the absorbance across the entire path length, it's not only detecting the HCl here and here, or like up here, but it's also now across the entire path length, which gives us an incorrect concentration, incorrect readings, because now the HCl is not supposed to be there. Path averaging as well dampens extreme temperatures. We have our hotspot in the middle, which is just a 2-centimeter path length. So obviously the outside of the thing is going to be a lot cooler. However, with the path averaging, because there's such a significant, most of the path is outside of the plane, the hotspot's going to be a lot lower than it actually is, or it's going to read a lot. There may also be the back and forth paths covering different areas. I mentioned we have a shield, has a little circle in it, just to make sure that we can cover as much of our cover as we can. But because with aligning a laser, pretty difficult, especially with such like minute angles. So we had to kind of do this, or back and then forth. So they're right on top of each other with a conical flame. This means that this bottom, it's not very representative. This bottom one is actually a shorter path than this top one, which means that the ratios aren't exactly 1 to 1 and cannot be fully compared. So that may give us, they may give us an inaccurate simulation. Plus, the extreme difference in pressure from nozzle to open air, noise equation, obviously pressure is related to temperature, so that big drop is going to cause a big drop in temperature. So that may not be equal to the internal temperature. The nozzle is not optimally diverged. The higher exhaust pressures do lead to line bonding and reducing the accuracy, as well as turbulent casting conditions lead to optical equipment vibration affecting results. These are picking up very, like the lasers are for very, very slim wavelength ranges, very, very sensitive. This means that any amount of vibration will affect the readings.
So yeah, that was if our data was incorrect, our temperature readings were just super off. And those are some possible ideas on why that might be. However, if our temperature readings are accurate to some extent, we believe that it's probably due to an inefficiency in the motor itself, which leads to some interesting conclusions. Some possible errors with the motor itself, as we talked about, very low chamber pressure. That reduces its burn rate significantly, which can reduce the overall operating temperature of the motor, something that's very possible. And then additionally, something that we've noticed a lot with our larger scale motors is that run the same propellant, is that it's not reacting with all of the aluminum. A lot of these motors tend to have aluminum coating buildup within the motor because the aluminum does not have enough time to travel throughout the motor and actually react with the ammonium chlorate before it leaves the motor. So some of those aluminum particles might heat up a little bit, but then carry that heat out of the motor before it packs. And then additionally, and then that is purely a product of the low L star for the actual motor itself. So something that we could potentially do in the future. If you want, next slide.
I would like to add something real quick. If that doesn't get correct, then the conclusion we can draw from this outcome after it's been verified is that this could be a very good method of evaluating our propellant and like our motor efficiency, because now we have all these different steps of where our motor may have gone wrong.
Sweet. Quickly going. Thank you for that. Quickly going through the future works in order to basically just redo this experiment, verify that it works, and if it does work, things that we can do with this data. Remake a larger test motor, larger L star, optimally diverge nozzle to where we're actually expanding to atmosphere, and then redo the test. Modify the stage, include vibration dampening solutions to reduce those inaccuracies like Grace talked about. Determine a temperature ratio to predict chamber temperature, right? NASA CA basically has chamber temperature about 200 Kelvin higher inside the chamber versus outside at the exit flame. So with our current data, it said it was basically, we were at like 1500 Kelvin. I'd like to be able to look and do some math to find a better ratio to determine, okay, here's our exit flame temperature. What function can we apply to that to get an actual chamber temperature? Then we want to be able to test propellants with differing formulations, different aluminum contents, and see also how burn catalysts and inhibitors play a role in our flame temperature and also the chamber temperature, burn rates, and all that. Write a program to take that raw data and process it automatically, because it is a bit of a slog to go through all that by hand. More accurate solid propellant simulation program. We would like to start looking at using ProPet or Cantera instead of NASA CA, because NASA CA isn't super well geared for solid propellants. And then in the long term, we'd like to start looking at potentially doing a fully non-intrusive propellant characterization, where we, instead of using the pressure and thrust relationship to characterize the motors, we use a temperature and thrust related relationship in order to characterize those motors. Quick acknowledgements, pretty much everyone in the LSCPL, all the graduate students of Oxford Mayor, and then the UTSA Administrative Faculty and references. And yeah, thank you for attending. Any questions?
Very quickly, did you find that there was any refractive phenomena when the laser transitioned from not in the flame to in the flame to not in the flame and back across, and changes in angle?
It's you mean in between tests, basically, like the laser position?
No, during testing, or did the laser beam refract any?
I believe so, just because I mean the detector is such a small area to reach it to, and the mirrors and you have to hit specific spots in the alignment, especially with 5 mirrors, is very particular. So if the flame did refract the light and change that angle any, it would number one maybe not have hit the mirrors and gone all the way through, but two, we were so close with the clearance of like the holes that it just would have hit the stand, it would have hit the shield. We were barely clearing a lot of things because we're trying to give us as much wiggle room as possible. So that angle, I believe no.
You said this was an aluminized propellant, and you know we could kind of see in the video the aluminum particles coming out of the exhaust. Do you think that you know any aluminum in the exhaust flame could have impacted your measurements?
Yes, we actually saw several buffers where the data looked good, and then it would just cut out and then keep going. And like there were chunks of phenolic nozzle. We use like little RCS phenolic nozzles, right? Phenolic nozzle aluminum particles, right? That would just unfortunately we weren't able to have as many buffers processed as we would like to because of exactly that.
Okay.
Go for it.
And then one more. Did you do any, I guess, simulation of your little F motor beforehand to compare at least like a burn time to see, you know, because you said, you know, maybe our chamber pressure is way off of what was expected, but you know, if you had that, you'd probably have a much different burn time than a simulation would. Did you do any?
Yeah, so I did burn sim of the motor, right? So we've actually tested this motor before, right, without all of this jazz, just as like a proof of concept, just can we make a motor? And it worked as burn sims said. However, when I had to make modifications for this experiment, I had to put a pressure tap in the back of it, and so it's a small motor, so that increasing volume there is what I believe was a large factor in what led to that decrease in pressure, as well as widening that nozzle to make it safe for a lab scale experiment. The chamber pressure in the burn sim was about like 100 psi, 110 psi. So it happened. Something about the way that it was modified happened, right? Or possibly just the inefficiency in the propellant itself that we just haven't picked up.
Another question.
We have 2 more minutes, so.
Anyone wants?
Yeah, we have lots of support slides as well. If you want to show those.
Let's go. Okay.
Yeah.
Spectroscopy fast. For those of you who are not familiar, this is the holy grail spectroscopy. We see a lot. It's very heavily researched, very established in spectroscopy. I researched our lab supervisor at the LSMP. He wrote a very similar paper doing something very similar of using HCl to characterize the flame. So I just borrowed his derivation, and there's this paper here if anyone is interested. And then just a brief explanation of what the virial limit law is. It's just for a non-uniform gas medium axial symmetry in R, CM, the virial limit law. It really is a bit of a definite gas to the spectral absorbance wavelength at a
One second, Grace, we have a question. I want to get this question.
I'll do another question. If you had infinite money, infinite whatever, would you choose to use that same wavelength and HCl as your species gas of interest again, or would you choose a different species gas and a different?
There is another one we could use. We could use carbon monoxide. However, carbon monoxide transitions line up very closely with water transitions. So that could cause some interference. If you had infinite money and infinite time and all that, or honestly even just 4 more months. We would have done a much larger motor and done it outside, right? And larger motor outside would have been great. All right, sweet, awesome. Thank you so much for attending.
And I would still stick with HCl. It's one of the easier ones. It's definitely established. There's a lot more data on it.
Yeah.
And the only issue is that it's very corrosive.
Corrosive, yeah. Yeah.
Like,
yeah.
HCl would be the best.
Build a bigger input or something like that. Yeah.
Oh, stop.
Yeah. Thank you very much.
Thank you. Yeah. No, it's
A lot of friends.
Really?
Okay.
For mini random laser.
Right. Yeah. Thanks so much.
You're welcome.
This is under
I'm sorry.
That's all right.
Okay.
Adam, okay, so we should explore. All right. All right.
Yeah. Oh. Wait.
Yeah.
Yeah. Yeah, from engineering plus you already thank you. Anything else? Other the other gentleman here, filling out the he should. Okay. What's his name? What's their name? It's all over. If not,
Yeah. Sorry, not much. You just did one. Like, say, 30 minutes.
okay, I'll bring you as well. They'll have 20 minutes for students and 5 minutes of questions.
Okay.
Okay.
Not there. Sorry, yeah. Curious, in the house before they. Yeah. Oh, sorry, I'm gonna try.
Hello everyone, my name is Ben and this is Dawson. We're part of Rocketry at Virginia Tech and we're going to talk about our team's active drag system. The active drag system is the ADS as we'll be referring to it, is what we designed in response to the altitude challenge of Spaceport. Since we're trying to get to 10,000 feet exactly, this is our solution to that problem. This year, we've gone with a flat design, shown here. This is our second major iteration of our design. In previous years, we used to use a push-out tabs that were a lot smaller. So the reason for our design increase the amount of drag we can produce and thus giving us a bigger control range.
And we also, one of the major things is we swapped our electrical design. Previously, we were using a single board computer written in Python. And this year, we switched to a microcontroller board written in pure bare metal C++ to allow for that more real-time response. That's what we'll be talking about there.
I'm going to talk about this year's mechanical design. It has a diameter of 5.75 inches, about 5 inches tall, weighs about 3 pounds. It's mostly made out of 3D printed ABS plastic. And there's several different components that I'll talk about kind of one by one here. The first being our flat, which we've made out of carbon fiber that we made in-house. To make those, we 3D printed a mold, 2 pieces, then we put carbon fiber and epoxy and laid it up, I believe 5 layers of carbon fiber. We clamped it together, let it sit overnight, and popped it out, and then did some sanding and post work. And that's the result. To hold those flaps in, we have these hinge pins at the top of these 3D printed columns that just work with these little pin and key pin things that let it hinge at the top so it can actuate. At the bottom, to push that hinge out, we have our track and ball design. That track we manufactured using a Loadcase, which was very helpful. That bracket is layered into the carbon fiber when we were laying it up, so it's nice and firm in there, it won't come loose. And then at the top of there is where we slide this ball in here, but we only use about 1 inch or 2 of the bottom there, so there's no risk of it coming out or loose of the flat. They actuate out to about 20 degrees from flush on the body tube, and the whole system is driven by our rack and pinion design on the interior down here. This center here is controlled by a servo motor that drives these 4 overlapping rack and pinion gears and these funny shaped pins that drive the whole system. So after we designed it, we sent it to our design validation sub-team, and they ran several tests and using CFD. They ran through a bunch of different speeds, I think between Mach 0.1 to 0.9, and then at different deployment angles, I think of 0, 25, 50, 75, and 100% deployment. And then they gave us all that coefficient of drag data so we could use it for our model.
Of the electrical design, like I mentioned before, we switched to a microcontroller as the primary flight computer. This year we chose to use a Raspberry Pi Pico for its ability to react pretty quickly with an interrupt-based finite state machine, as well as it's clocked pretty high at about 133 megahertz. It's got 2 cores that we utilize for multi-threading primary deployment algorithm, as well as logging data to an external flash chip. That can be seen on the backside right there. For one of the major circuit interesting components of this PCB is, we all know the rocket's going to sit on the pad for quite a while. So one of the main things that we saw was the servo, even just idle current, was rather high. So in order to mitigate battery usage when we're not actually trying to deploy anything, we have this optocoupler circuit where essentially the Raspberry Pi drives the optocoupler high when we detect that initial launch event, which I'll talk about in a little bit with the finite state machine, to
complete the N-channel MOSFET circuit. It closes, so basically the optocoupler acts as an opto isolation between the Raspberry Pi Pico and the servo, because we've had issues in the past where there's flyback current from the servo due to the higher voltage battery that we use for it. The other notable things on this PCB are we use two Adafruit like breakout boards for the B&O 055 IMU, which we obtain accelerometer and gyroscopic data from, as well as the MPL altimeter. It's a barometric based altimeter, and that's the primary use for our finite state machine. So that finite state machine, essentially, when it sits at the pad, when it boots up, it's in the no flap deployment. It has not enabled that MOSFET circuit that I just mentioned. The flaps are just being held in place essentially by the mechanical design that Ben talked about. It's primarily driven by an external GPIO pin that it's watching, that the altimeter can drive high at certain altitude thresholds. The primary one is the first one that we set at the beginning of enabling. It will take a measurement of the ground altitude, and then it'll set an interrupt at about 100 feet off the pad, and that's what it uses to detect that initial launch event. At that time, it will complete the N-channel MOSFET circuit and suck the fins, or the flaps in, so that we ensure that there will be no flap deployment during the boost, so that high torque servo is going to be fighting against basically the air resistance. And then we also have a redundant check of the 2.5 Gs with the accelerometer. For the coast phase, we have a burn timer. Once the boost phase has started, we start a hardware timer that's currently set for 4 seconds, which is about the burn time of our M2500 motor. And then once that hardware timer elapses, then we do another vertical acceleration check. And once we see that it has reached approximately under 0.9 Gs, then we will determine that we are in the coast phase, which we can run the deployment algorithm in. So the deployment algorithm essentially is in the previous iteration from last year, we had a student develop a correlation between the CFD simulations and the coefficients of drag that we obtained from our design validation team. He developed a correlation between that and then also a best fit model of what we would imagine is a perfect flight, where we fly on the M2500 to exactly 10,000 feet, and that's our apogee point. And so he developed a best fit polynomial model that we just provided a altitude and a velocity, and it outputs a deployment percentage. This was all done in a pre-computed MATLAB script to limit essentially the computations that are going to be happening on board the Raspberry Pi Pico. And in order to get an estimate of that vertical velocity acceleration, we have a homegrown Kalman filter to fuse the altitude with the linear acceleration that we obtain from the IMU. And so basically our most important part of the state machine is knowing when this state happens. We just need to know when boost has completed, then we can start actually deploying the flaps. And then the apogee, essentially when velocity has crossed that negative threshold, that's when we suck them back in, just for safety purposes as well as for preservation of the actual flaps themselves. And the rest of these states are essentially just for logging, which we, like I said, we do in a multi-threaded fashion. They're in 32-byte serialized packages that just are sequential data bits where there's altitude here, velocity here, acceleration here, and so on with other measurements that we take during flight. And the Raspberry Pi Pico features a second core that we do that on, and we initialize it at boot. On the pad, it will just log to a buffer so that we're not basically wasting space while we're waiting on the pad. There's a circular buffer that it just is logging to,
And then once it detects this launch event, once we go from pad to boost, it'll just dump all of the, like, I think it's about 2,000 bytes, so about 2 kilobytes of flash. So at the rate that we're going, we're logging about 10 times a second. We're updating the state machine about 100 times a second. It will dump all of the last like 8 seconds or so of the like altitude and accelerometer. This is a little more about the algorithmic deployment percentage that we determined last year. So like I said, we established like correlation between the coefficient of drag as well as like our ability to control the apogee. So we had a couple like models that we utilized. One is the like constant air density model and the standard atmosphere model. And we basically adjusted for when we're having like the current climb rate, like how close can we get that best fit curve of the like altitude. And so we determine the optimal coefficient of drag. And then this is a graph of the algorithm in action. The main portion to look at is right here. That would be around where the post phase occurs in a open rocket simulation of our design. We input altitude and velocity, and it provides us a deployment percentage. You can see right in the open rocket simulation when it determines the aptitude up to an extremely high percentage. So in the actual software stack, we plant it from 0 to 100% to make sure that it doesn't attempt to try to deploy the flaps any more than they physically can. So these are the results from one of our test launches. You see in this 3-picture like little timeline, we were able to verify that the flaps were able to deploy successfully. We were able to also determine the ability of the state machine to determine those flight stage events properly. There's a video that corresponds with this that I wasn't able to put in here, but essentially you were able to see right at apogee. It would also suck the fins right back in right after the like almost in line with the ejection event. And as well as this point, we were operating without the IMU. So we were able to determine that in case of the failure mode of the IMU not functioning, it was able to safely deploy and retract on purely altitude data. And we introduced the Kalman filter following this launch. So follow-up work, one of the main things is we have gaps in the structure of our rocket to accommodate those large external flap designs, which should hopefully reduce those airframe gaps due to the flap installment. Currently, it's because of that pin design to secure it as much as possible. I'd like to look into reducing the PCB size as well as the dependence upon like those Adafruit boards or development boards such as the Raspberry Pi Pico. And I want to basically move more of that MATLAB computation onto an on-flight computation. Because I found that the Raspberry Pi Pico is a rather capable board that is able to be incredibly reactive, especially when you're operating with the interrupt finite state machine where everything is, as soon as it detects that pin high, it sends that launch event and it sends that that hardware timer into play. Same with when the hardware timer elapses, it does that. And the reason I say 100 hertz is it's basically taking in new measurements at that speed. It's got an onboard I2C, works to our advantage.
harness. It was, you have a plot on the right that I'm trying to understand. This one? Yeah. Can you talk me through that?
Yeah, so this up here is essentially a graph of the state train. So right here you can see where we started logging is at the pad, and then motor burn. And this time we were flying on an L motor, so it was a longer burn time than we have now. And then you can see that once it hits this motor burn, it instantly goes to the coast phase. And then the Apogee's similar thing. Apogee is really only there for just logging purposes. We just need to know when to suck them in. Altitude data, this is also unfiltered data, and same with the velocity values. You can see this was prior to the Kalman filter, which explains the insane spikes that you can see.
Okay. So that's real. Is that logged on board or telemetry back?
Yep.
Where you transmitted that data?
We're not transmitting this data.
Okay, so it's onboard logging.
Correct.
Okay, and those are dropouts of the IMU, or that's actually it?
That's so. And during this test launch, we weren't operating with an IMU.
Okay.
The IMU had failed right before the test launch, but we had tested this in a vacuum chamber as well several times over to ensure that, essentially what you do with a standard altimeter, just to see that flap deployment. Whereas in altimeter you would hear the beeps, but yeah. So this was when we were operating on essentially just taking altitude values and taking the delta time, and you can see the impulses that you get when you use that.
Sure. Okay, makes sense.
Yeah.
How was your performance for that test flight versus the CFD models that you ran when you were talking about earlier in ANSYS? Were you guys able to draw any?
We haven't been able to do a ton of checking with that just because we haven't been able to run the full algorithm on the test launch. Like I said, this was just a test of the mechanism and some of the electronics.
Okay.
We were planning to test the whole algorithm during a test launch a few months ago, but due to weather, we were unable to launch. So we're going to try to get that kind of data tomorrow. So
yeah, so talk me through your post-flight analysis plan for the data tomorrow. What are you looking for, and how are you going to feed that back in to refine the system?
So, sorry, excuse me. So basically, I have a set of tools for this code base, where one of the main ones before flight, we have to calibrate the IMU because there's some drift when you just leave it sitting for a while. So those are just essentially, we calibrate it as its own tool and then drop in those offset values. And then one of the other tools is actually just a data dump of just reading from the flash. So it outputs a CSV file, and then we can send that through. We have a couple of more data analysis people on the team that can run that through their MATLAB scripts. And I know one member of our team was talking about taking a Fourier analysis and just seeing the effects of our in-house Kalman filter and the high data rate that we're operating at. So
okay. But you have an IMU on board for the flight tomorrow, so also you should be able to compare some of the deceleration values versus what CFD would predict.
Yep, correct.
Yeah. Anybody else have any questions?
How'd you go about tuning the Kalman filter?
So that's actually a little out of my wheelhouse, but so I didn't mean to switch slide. The Kalman filter, it's just a standard two-variable Kalman filter with the IMU linear acceleration variable. I've done some research into hopefully moving on to more primary Kalman filter with a complementary Kalman filter to integrate the acceleration in a better fashion, especially with gyroscopic data. But I'm not sure. Usually you would tune more of a PID than a Kalman filter.
I meant specifically the covariance matrix.
Covariance matrix. Yeah, so we use just generally we research the sensor variance and just drop that in. Obviously, like we said, we weren't able to operate on a test flight to adjust that afterwards, especially with the IMU.
But we use just because the sensors are very like commonly used, we just use sensor offsets that covariance values that we obtain from like certain forms.
So you mentioned that a previous iteration of this project had your breaks push out. Have you been able to do any kind of tests for validation to make sure that this new design is actually better at targeting the outage?
Yeah, the old design was think about like 2 square inches of area on each plot. This was like 20, so it should be, but and before I think on all of our altitude data, we could not see any sort of effect when they came out. But this year we've already seen that on that one test flight that there was some change in the velocity.
So then as a follow-up, the 20 inches that's per
flight.
Flat, right? Was there like formula used to determine that, or was it just?
I think it was kind of a pretty rough estimate at the very beginning of the year. We were just kind of like our goal was to be able to take off 1,000 feet of altitude if we had to. So if it was like deployed out the entire crew space, they would take off 1,000. So we kind of did some rough calculations for that to just get an estimate, and we'll validate that more once we fly it. But
yeah, I just was curious, was there any thought to the ABS plastic for the material versus like a ETG plastic or any other type of filament?
The main reason is just that it's a little bit stronger than what we usually use PLA, and the melting temperature is higher. So since we're in the desert, we just better safe than sorry. So, but yeah, it's just a bit stronger and just a little bit better. Since a lot of our design is load bearing within, like all of this holds all that rack and pinion in. So when the flaps are pushing on it, it needs to be strong, not static. So. Any other questions? All right. Thank you guys for.
No way, I'm just like between my products. I won't be able to do
Robert is all. Alright, you think as for the resolution classes.
We need to go. Oh, okay.
Thank you. Thank you.
We'll chat.
All right.
Yeah. Yeah, we'll try to be there like 4:15 would be like.
Thank you, guys.
We can do the other ones first.
No, I just have. I go with this. So we just say another one.
Yeah, so we have this PlayStation 38, and then we go to
Where'd you?
So
that's
yeah.
I don't know. I'm gonna be doing wires. Yeah, well, there's a wires.
Thank you. Good evening, everyone. I'm here today. Yeah, just for ideas on the regular water. We're gonna think on these modules, earlier. Yeah, thank you. All the things Disease games. Well, he's played by especially two weeks ago.
Hello, everybody. We're gonna wait just a little bit.
Hi, John.
Glad people are interested.
We don't launch that on
So yes, U-Rock, it's just west of Eagle Mountain, which is a bit south of Provo.
Okay.
It's one of our two launches. Small scale. A lot of launches. Yeah, change. Yeah, I mean, they also use a lot of A dimension on myself, but it's like I've been around, just trying to get as many sets as we can. My dog. Yeah. Makes sense. We're hanging and then burn back with frosty. But the reason why approximately for all right, hello everybody. Today we're going to talk a little bit about simulation and control, and particularly our team's approach to the problem. I've seen a lot of you around our table. Glad you could come. Glad you were interested to hear more. But let's get started. So, what brings us all here today? A table of contents. It's not filled, apparently. What brings us all here today? A competition where we are launching rockets to a designated height target. Our team is participating in the commercial off-the-shelf 10K category. So what we're more focusing on is less the propulsion system and more everything else that goes around, in particularly are variable control. We want to be able to do this in any weather, any particular situation. So typically, there's going to be two different strategies for slowing your rocket. You're going to either ballast, add more weight until your simulations and your open rockets or RASAir, whatever simulation software you choose to use, until it shows that you're hitting really close to that 10K mark. Or a lot of teams are using flap systems. Flap systems are able to allow you to overshoot your target and then correct down to it somehow. To do the first strategy to ballast, you need simulation software. Open Rocket and RASAir in particular, those are free. Everybody has them. I'm sure most people in this room are familiar with them. Who hasn't used either of those in this room? Like, I can't.
Doesn't count.
So, these will maintain their trusted tools. That is what allows a high confidence for the ballast. But what about the flaps? Suddenly, we've introduced a part that is difficult to simulate. RASAir offers a perturbances feature where you can stick a cube onto the side of your rocket, but that doesn't really simulate control. So that's where our SRED simulator comes in and fills in the gaps. The control, the simulation simulates controllable flaps. That is ultimately the goal. So how did this come into being? I will give you one hint. Love math. And math never ends well. This is the result of math, I assure you. Starting off, simulation is built upon differential equations. You need to know how something is going to move to know how to do it. Our approach uses ballistics. So that means we're going to start with a point mass. What is that experiencing? We're experiencing gravity, and we're experiencing drag. Well, that's pretty straightforward, right? It's just two forces. What is drag? What is drag? That is the problem. Well, the rho v squared AC cross-sectional area, drag coefficient, cool stuff. And you're like, we can do this. Well, coefficient of drag, that's experimentally determined, and it varies depending on how fast you're going and the air composition of the winds of the gods that day. And yeah. Furthermore, as you go up, the atmosphere changes, and so there's a couple more easy differential equations for us to pop in. As we're going up, our vertical position is changing. That's the R that we keep seeing, and that allows the standard atmosphere model gives a very good approximation for a linear temperature and linear pressure distribution. And then you throw it all together, you're like, oh my god, we solved it. We can control a rocket, right? No. What am I looking at? I can't look at this personally and understand exactly what I'm supposed to do. And so that's where we kind of throw it in a picture and be like, yeah, just do it for me. Has anybody here used Simulink or is familiar with MathWorks and MATLAB? Quite a few people, that's good, yeah. I am known on the team for being a, what's an appropriate professional way to put it? A suck up to MATLAB. I thoroughly enjoy their products and find it to be a good working area. So let's get into this flap drag controls simulator that I made. I'm going to be going through some Simulink stuff, but it is just as easy. Well, okay, not just as easy. It is just as feasible to do this all in a Python or a C++ or anything, as long as you solve the differential equations. Because all this is it's revolving around the differential equations. RK45, Euler's method, something along those lines. But here's the high-level approach. This is what it kind of all looks like thrown together. You got a launch button, click for that to go, and then you got, oh my god, we just got 341 points, we're gonna win. And then you just like all the blue stuff go and leave touch. So, like I was saying, this is not specifically Simulink. Anybody with the mathematical background in this room could make a simulator to be performance. So specifically, let's talk about the capabilities of mine and what I did. So like I said, I used ballistics instead of trying to figure out, oh, if I put that much force on the fins, I'm gonna curve over and our trajectory is that way. No, we're going straight up and we're wind vaning into the area. So that allows us to use at the core a two-step integral. If I give you the forces, you can give me, solving the differential equations, our position, our velocity, and I gave you acceleration. So that's what this section is, and then it feeds it back in over here, and we calculate our pressure differential equation, which is a linear scaling thing with time, and our temperature differential, etc. And then there's one force that it all feeds into, and that is the drag. How much drag does air make? Well, it makes as much as an air drag drags. So we just zoomed in on that block in the middle. This is what it looks like put together. Please, there we go. The body frame drag. The biggest thing is I can figure out that cross-sectional area. That's a circle. Easy. Next problem is coefficient of drag. I already said that varies with Mach number. Well, it turns out that there is a military database of like tested sounding rocket geometries with their wind tunnel and all sorts of information on that. And RAS Aero uses that for their drag calculations. And furthermore, if you put your rocket in RAS Aero, it can spit out a plot of coefficient of drag as a function of Mach number. So what we do is we slap that in our simulator, and we use a linear interpolation, a lookup table. And so given my Mach number, I now know my coefficient of drag is velocity. And then our rockets tend to have imperfections. It's not a perfect suit. I've drilled holes, I've put cameras on, I've had flaps rolling all around it. And this term is immediately like, oh, I have a CD of 0.7. Wrong. Now I have a CD of 0.7 because it's plus 0, but it could be 0.8 because we added a number to it. And so by adjusting this, by playing with how much additional drag we have, we can see the effects of that. Flaps. Here's where things get interesting. This is what we cared about more. Why, if we're using a RAS Aero lookup table, why aren't we just running RAS Aero simulations? Right here is where that happens. A flap is, approximately speaking, a flat plate perpendicular to flow, if it's fully extended. Our system uses like penguin style flaps, so they extend like that, come back down. And so if it's approximately a flat plate in flow, then we know from our fluid dynamics textbooks that once you know that's approximately 1 or 1.2, depending on your approximation of the geometry. Ours is a bit curved, so that's why we've reduced it from 1.2 down to 1. And if it's going up penguining around a hinge, that's a circle. So let's multiply that by a sine. And we verified that relationship by putting our small scale rocket into a wind tunnel. And we found approximately that as the flaps extend, there's a sine circle relationship. So we plug that in at 0 degrees left, there's 0 effective drag according to that. And at full flaps, there is approximately 1 coefficient of drag for that. And we multiply by the geometries, and then we collect those two, the body plus the flaps, and we assume that interactions between them are linearly negligible, slap them together, and now we have our cross-sectional area and our coefficients of drags as contributed to by the rocket and by the flaps. And there's some other stuff with some coordinate frames because of mostly wind condition stuff. But Mach number, velocity squared, and this is a very crude approximation of wind. If I have air going against the fin and the body, then it's roughly going to try to push it that way. And once we apply that concept to our rocket coordinate frame versus our origin coordinate frame, we can now do matrix multiplication to figure out the overall effects upon the rocket as it flows through. So here is the rocket orientation determination. So again, the assumption is that we are perfectly following a ballistic trajectory and wind vane. So that means whatever my horizontal velocity component is and vertical velocity component, those determine my orientation as well as direction. So we're always head on in loop. And so again, pulling it all together, we take in velocity and wind, we take it to consider what direction we're going, how fast we're going, and we feed it into our drag approximations. We multiply it by our orientation, and we get out at the very end our acceleration due to drag. So again, the assumptions are a linear atmosphere, the standard atmosphere. The the flap drags, I used the constant number for a plate in flow. I did not adjust that for mod. That's another important assumption. And then the biggest features we've acquired is now the flaps can vary according to angle. So now that we have flaps that vary according to angle, we've put our acceleration into that two-step integrator at the very beginning. We have position and velocity. We can now go back and feed acceleration, velocity, and altitude into our controller. We're going to skip over this part, but regardless of how you control your rocket, right here is where you can do the math. If you're using state space, PID like we did, or anything else, you've collected enough information at this point in your simulator to put it all together. And as long as you get out, here's where my flaps. And then finally, to tie it all together, we have a state machine controlling the simulation. So until I push the button, we're not doing anything. I push the button and then the motor ignites. Then it burns out, and now the flaps have to start moving. Then we hit apogee and everything. Motor thrust curve. This is publicly available information. You get your, unless you're doing SRED, then you have to come up with thrust curve yourself. I'm sorry. But you take the thrust curve and the integral of the thrust curve, put it against your flight angle, and you can get the force due to your motor. And then we take the integral of the thrust curve so that we can multiply it by how far along the motor has burned, so we know how much mass we have gone through, and we can subtract the correct amount of mass from our rocket. All right, now we've thrown it all together. Now we can start tuning our controller. So here is an example of a simulation I was running just last night, where I was comparing three important parameters. Obviously, we have altitude on this side, and the colors correspond to that RAS arrow drag offset that I was talking about. As this is verifying that for any amount of extra drag we put on the rocket by accidentally leaving holes uncovered, that we are still able to hit within that 20-foot span. And then each clump is a different calibration of our control algorithm. So this one did not perform as well as the other three. So what exactly did we do for controls? This is another part where our team took it in a pretty unique direction. Instead of, okay, for the challenges, the controller can only go one direction. Your rocket burns once, and then from there, you can't add more energy. Your flaps can only remove it. And it is because of that it's unidirectional control, and control algorithms don't like that at all, from my experience. And so the next problem is, as you're going up and you hit apogee, your rocket doesn't want to stay there, it wants to immediately come back down. Trying to control rockets to do that requires some tricks. So the most common approach, I might think, is a modern controls approach, such as controlling to a trajectory or controlling to a point.
who's taken more advanced controls, like linear multivariable type classes? Like maybe 5%? That's exactly the problem. These concepts aren't really taught to us until later in our careers. That is another reason why we really wanted to try to force this problem into a classical controls. So the math gets really ugly really fast if you try to do it this way, and even after we tried to do it this way, we forgot a part of the linearization process, and our control algorithm didn't account for the speed that we were able to open and other such problems. So when we're doing this, we need to be able to linearize, we need the trajectory, it needs to be time constant, and this problem just is not fitting in this concept. Instead, we will embrace classical. We will return to the PID that rules us all. And to do that, we need to comply with those characteristics. We need it to be going to a 6. Unlike modern control, where you can kind of arbitrarily, well, not arbitrary, where you have more ability to play around with this, you must have a steady state. Furthermore, the controller will either want to overshoot, oscillate around its final value before settling, or it will very slowly reach up to the final value. So that's either overshoot or time. Well, in a rocket launch, I don't really have time, so I guess I'm going to have to work around overshoot. Well, if I overshoot, I can't re-add the energy back. And so that's where the challenge comes. So what we've done is the control algorithm forces this into a steady state by looking at that energy. Think back to physics 1. If I throw the ball, how high will it go? There's a couple different spots you can ask, well, how fast did you throw it? Or like, what angle did you throw it at? Or really what it comes down to, the fastest way to do it in that level is energy. I have this kinetic energy when I start. I have this potential energy when I start. Therefore, I'll have this total energy at the end, and I will be able to get this high. Knowing that information, let's plop that on the simulator and see what happens. At every timestamp, I've calculated the potential energy in the system. It goes down? What? That's not what we learned. It's because of drag. We need to characterize the drag. So what we did is we noticed that this natural response, this is no flaps whatsoever. We start with a lot of energy, we decay, and right around here, right at around 15 seconds, we are rather stable. That's the steady state we were looking for. So now what we're going to do is we're going to pop on 10K and be like, go to that. No, we're not there yet. Instead, we're going to define our own drag curve. And so what we've done is we match the initial energy and we match the decay rates. Again, at about 15 seconds, we're at a steady state with this equation. But the natural response ends at 1,100 feet, whereas the force of the desired equation ends at 10,000 feet. And so now we turn on PID, ask it to go to, instead of 10,000 feet, ask it to go to 1,100 feet and progressively get lower. And the controller is allowed to oscillate around that target and then settle out by the time it's reached the bottom and we lost control of it. And so here's an example of how the flaps might try to respond to that situation. Again, all these graphs are made from that simulator that we're showing. And here are some test launches that help us verify the results. Here is our Montana launch. We had a bug where it started a little too soon, so the timing was off and kind of bit overcompensation, but you still see a good time. And then in our full-scale launch, we had a problem with the barometer not sitting properly. So it was too sealed at the beginning, it finally gets close, opens up the flaps, and it's like, oh my goodness. And then it opens up the flaps a ton and ruins everything. But that's our approach. Questions, things you'd like me to go over? Questions? What's up? Yes, sir, in the back.
I don't fully understand fusion.
Fusion?
Between your differential, before differentiating and integrating two variables, and how you get rid of all the noise.
The differentiation and integrating the variables.
Yes.
In the simulator, in the actual product.
Yes.
Okay, so the simulator is the simulator is noises. In the control function, we actually inject noise to test the robustness of the controller against noise. So the only thing experiencing noise is the control algorithm. The rest of the simulator is giving us actual values. Yes, sir.
Kind of on a related topic. Typically with PID controls, the derivative term is very susceptible to noise. It's hard to do. So what made you choose a PID versus that?
So yes, PID was chosen for the sake of this presentation because it rolls off the tongue. In actuality, it is a PI control. And it is actually predominantly just the proportional term. The integral term does very little in this application because there's so little time to get to steady state. However, adding a small integral term we found helps with that robustness factor.
How many hours have you run simulation?
My computer has run many hours. Remote into my PC at home because my little laptop right here is it screams in pain and agony. It takes two minutes to generate the amount of simulations that my other one does in 10 seconds. Yes, sir.
Could you do could you explain a little bit more about the actual onboard system that's controlling the flaps for this?
Absolutely. So we rely on an accelerometer and barometer. So back in my earlier slides, you saw in my control algorithm a feedback AVT. What we don't actually use V, we just use A and H. That's because that's the information we have available to us. What we do is we project the acceleration onto the vertical orientation, which we track using gyroscopes. Then we subtract the effects of gravity, and then that gives us the force of drag predominantly. Knowing that is our vertical acceleration, we can now integrate it, and that integral is the velocity that we need. Then we take the barometer data, take its derivative, and that also gives us the velocity we need. So we take a two-part complementary, there's a buzzword for it, it's like a fusion something or other with two sensors, where every time you calculate the dt times the height for your sum, your integral, you also add a weighted factor of the derivative of the barometer. And they both combine in such a way that you get the smoothness of an integral, but the accuracy of the derivative, but not the noise.
So your test flights, you've done numerous test flights with both the smaller diameter and the larger diameter vehicle. How have you fed that data back into your model? Tweaked your coefficients to match what you're seeing in flight?
Absolutely. So during these first couple flights, we saw, so this one doesn't have a picture because flaps failed to open. The one right there, I think, one of these two, the flaps opened briefly and closed, but the final one was a successful launch. That's the Montana graph where it was kind of slightly delayed. After adjusting the simulator to account for the delay, it gave the same number within 10 beats. And then the other one had the pressure spike. So that's our searches. Every single launch, we ran simulations using open rocket raster and this guy. And that's all the time we have. So,
Hey, come on,
Ja, je muss
Step down.
Nice work, John.
Guys, very well.
Yeah. If you guys need, thanks for coming out, guys. Good job. Appreciate it.
Let's do it up to the sides, you guys.
Yeah. Oh, yes. Oh.
Oh. Oh. Okay.
Yeah.
Oh my gosh. So.
Oh yeah, I have which makes it infinitely less.
That's so true.
Of course he has one. That's so.
Maybe there are two people who are holding the camera on the stand.
Yeah. Yeah. Especially since I didn't come at the front.
Also, that's not much. Hey, shut.
Well, we can fill in what's more. We're here. Which on a 5-minute break. It's got a screen.
If you want
I mean, it's like super unorthodox.
Yeah, two total. I know, but it helps us communicate.
Like a
I think it's small. What?
Is anyone a Chihuahua person like Chihuahua tolerance?
There's like no, I don't personally.
Yeah, but they can do that for a loop.
Yeah.
That's
Or just like convert it back.
Well, the camera's it's just going to
And they shouldn't have done that.
Yeah.
Well, they're yeah.
In a future.
In response to urgent message.
Oh, we need to make sure to be quiet. Camera or the microphone.
Hi, Archie.
You got a good go.
Alright.
I miss you, Archie.
I'm Benjamin Peters. I'm Will Shirey. We're representing the Worcester Polytechnic Institute High Power Rocketry Club, or Team 151, you see us out on the floor. I am the ground station team's hardware lead. Ground station team is dedicated to telemetry, antennas, and live visualization systems.
Yep, I am in charge of our ground station software, so the software side of those systems. So our telemetry overview, this year we'll be using the Digi XB radio modules. So these radio modules feature frequency hopping to avoid channels that might already be in use or channels that have noise. So they'll automatically avoid noise that's already in the band that they operate on.
And they also have mesh networking, which they do automatically as well. And so mesh networking will greatly improve the ability of radios to communicate with one another, even if there's no line of sight between any two. And mesh networking also allows for communications to be sent and delivered as quickly as possible and with as much power as possible. So you get more range and quick communications. This year, we'll be using our custom RB2040 based flight computers for data collection, our state estimation, and our air brake system. So this flight computer, custom built, and it runs at 40 hertz, which is 40 times every second, pretty fast. So being able to transmit and receive as much of that data as possible is pretty crucial so that we can go back afterwards and analyze the flight. And this year, we'll be using student-designed transmission and receiver antennas. So transmission, receiver. And the receiver itself is actually built by us. The team has spent many, many hours researching, designing, and simulating antennas to find the best fit for our situation. So we also took into consideration different environmental factors because the environment can play pretty big role in radio communications and their signals, depending on different situations. So at Spaceport America, which is what we mostly designed for, we're launching away from any populated areas. So that means we don't have to worry about large buildings or any big vehicles that might interfere. And there's also reduced natural obstruction. So there's no trees, there's no large rocks for the most part that we have to worry about. So there's also mostly sand and dirt, a little bit of scattered brush and bushes. But for the most part, Spaceport America is a pretty ideal place to have radio communication. There's really nothing we have to worry about. For example, if you're in the city, you might have to use frequencies that can penetrate large buildings, which, as I'll talk about in the next slide, there are high frequencies can penetrate large buildings, but there are some drawbacks as well. So that leads nicely into band selection. So what is a radio band? A radio band is a range of frequencies that are allocated for use for different purposes. So, for example, there's the FM radio band, which is between the 88 and 108 megahertz range. So FM radios use that band. And so there are all different ones. For rocketry, common bands are the 300 megahertz band, the 400, and the 900 megahertz band. And so, as you can see in this chart, there are drawbacks to each. So as your transmission frequency increases, your range also, your data rate increases, so you can send more data with higher frequencies. But at the same time, your range decreases as you increase your transmission frequency. So like I said, if you have a transmission that needs to go through a large building, it needs to have a high frequency that allows it to penetrate that object, but then you'll get attenuation and it makes the signal able to travel a lesser distance. So there's drawbacks to each. And so for our consideration, we wanted to find a frequency that gives us a high enough data rate so that we can get as much data as possible, but also a low enough frequency that we can receive it with strong gain from very far away. Our rocket, a 10K COTS beam, so it'll be going up to 10,000 feet, and then it'll be drifted potentially, so it can go pretty far away. So for our use case, we decided on the 900 megahertz range, which is a pretty common band for rocketry teams to use. It's part of the ISM band, the Industrial, Scientific, and Medical allocation. So it's a happy medium of range and data rates. So we get easily enough data as we want. The XP radio modules can transmit up to 250 kilobits a second, and they can transmit up to 100 times every second. So we need most of that for all the data that we collect. So the 900 megahertz range is a pretty happy medium of range and data rate.
All right, so now jumping into the actual design of the antennas themselves. When we were designing the transmitter, we had two main options, and I think we might have a little bit of a spoiler for which one we ended up selecting, but don't look at it until we get it. The two main options were the blade dipole and helix antenna. There are drawbacks to both, as well as advantages to both. For instance, the blade dipole, which is composed of two leaves that make a dipole between them. Here you can see the two leaves, upper and lower. is a large flat plane, which allows us to manufacture it as a PCB antenna. The PCB material itself gives the antenna more strength to withstand the vibrations of launch, while also, due to our choice of material, not blocking RF signals. It's actually a fiberglass material that doesn't block RF as much as standard glass as well. There are other advantages to blade dipole. It has very high bandwidth, which means we can transmit over a large range of frequencies without sacrificing too much power. This is important because, as Will mentioned, we use a frequency hopping transmit, so we need that bandwidth to be able to effectively transmit at every frequency. If we were just using a frequency hopping transmitter that's good at one frequency, it wouldn't be much use to avoid the noise because everything other than that one frequency, you lose so much power anyway. The radiation pattern is also nearly omnidirectional, which we'll get into that a little more later, but essentially it means we don't have to use a lot of complex simulations to determine exactly where we need the route to be for the antenna to be effective. On the other hand, the helix tends to be more hemispherical. That means we position it and it'll either transmit well above or it'll transmit well below, depending on the orientation and twist of the wires that make it up. But it's much more fragile. It's typically made of a set of wrapped wires. And at the scales that we would need, this is kind of difficult to maintain structural stability that a single PCB gives us. One idea we did have was that if we could match the radius just right and impedance match it, we could actually integrate it into the airframe itself, since the airframe is already cylindrical, but that was deemed to be too complex. And in the end, we chose to go with blade dipole, as you can see right here. Now we'll get into some more of those considerations I mentioned. The VSWR is the voltage standing wave ratio. It's one of the primary considerations in antenna design. It essentially represents the ratio between the maximum height and minimum height of a standing wave that can build up inside the transmission line. Well, effectively the amplitude of it. We want it to be as close to 1 as possible because that would mean that the minimum point, the valley, is equal to the peak of the wave, or in other words, it's just a line, no wave. Which is why you see 1 at the bottom of the chart and going up from there. We were able to optimize this to the point where, as shown here, over a frequency range of interest, which is 900 to 930 megahertz, nowhere does it exceed 1.09, and for most of it, it's below 1.065. For reference, the commercial standard for antennas is approximately 2, where VSWR 2 represents approximately a 15% loss in radiated power. When the standing wave builds up in the transmission line, this actually will deflect power back into the transmitter rather than radiating it, which can not only cause a loss of power as mentioned, it can damage a transmitter over time, leading to failures during the flight. The other main consideration when designing an antenna is the radiation. The radiation pattern essentially is, when we put power into an antenna, it's not going to radiate that power equally in every direction. Theoretically, an isotropic antenna, which is one that radiates in every direction, is actually physically impossible. But our goal is to get as close as possible so that no matter what orientation the rocket is in during flight, no matter what orientation it lands in, we'll still have effective radiation towards the ground station. Essentially to make it so that there's few regions as possible where the radiation is significantly dampened. As you can see, we only have 2 nulls, that is regions where the radiation is significantly reduced, and those are directly on the axis here. But since our ground station will be located away from the pad, as well as since the rocket will be flying on a ballistic arc, we do not anticipate that the ground station would ever be located within that 10-degree cone for more than a few seconds, and even that would be unlikely. As you can see, the radiation pattern is most effective around the horizon. This is good for when it's on the pad, and may be good when it lands. It depends on the exact orientation of the rocket, but here's to hoping, right? If you imagine this being rotated about its axis, that's the full 3D radiation pattern. We chose to display it like this because it lets you see a little more of the details of it broken down. As mentioned, blade dipoles in general are nearly omnidirectional, and we've had experience building them in the past, which is why, in the end, we selected a blade dipole for the transmitter. Moving on to the receiver. That's this tall one over here. We had a few design considerations when we were going into the receiver. Unlike with the blade dipole, we wanted to build a new design of antenna, as we've had success with our previous helical receivers, but not as much success as we'd like. So the main design considerations were the elevation optimization, which is a lot easier to do with the receiver than it is with the transmitter. That's because as the rocket flies, the transmitter could be in any number of orientations in addition to its position. On the other hand, the receiver has a fixed position and fixed orientation, meaning there's a lot less simulation we have to do. We only need to know the position of the rocket in order to determine the incident angle rather than the position and orientation. Where the orientation is much more difficult to simulate, especially during the descent phase when it's going to be oscillating under a parachute. Though we know in general it'll be on average upright because it's suspended from one end. Overall, we determined that throughout most of the flight, the rocket should not exceed 60 degrees above the horizon, and obviously will never go below the horizon unless we accidentally set this up on a slope, but we're doing our best to avoid that tomorrow. As a result, we actually want to minimize radiation from below the horizon while maximizing it in that 0 to 60 degree region. Which led us into this. This is the double-cross dipole. It was designed for satellite communications, and satellite communications actually shares a lot of characteristics with our desired use case, which is amateur rocketry. Satellite communications, just like amateur rocketry, you're not very often going to have your rocket directly overhead, and you're not very often going to have satellite. The vertical path will usually not cross over you, even when you can still see it. And likewise, the satellite will likely not be below the horizon when you're trying to receive from it, because then you won't be able to receive. Satellites typically require line of sight just due to how far away they are. So yes, this was designed for satellite communications, and we actually were able to enhance it with the use of a reflector panel, which I will get into now. The way the reflector panel works is when you have signals that are coming in at some incident angle above the horizon, the reflector will reflect them back into the four dipoles here, reflect it back in such a way that it constructively interferes with the original signal, enhancing its reception. On the other hand, depending on a lot of characteristics, the ground, the exact incident angle, things like that, you could be getting ground reflections, which will often destructively interfere and are much more difficult to predict because the ground is a much larger area and is not as uniform as a reflector plate. So the reflector plate will actually block out many of those ground reflections while enhancing the direct signal, which is what we were going for. It'll also block out local interference, which is a very important characteristic. We've had a lot of issues with local interference in the past, and this is something that's going to be common to pretty much all amateur rocketry applications, as there's just so many teams, so many electronics in the area, especially in the 900 megahertz band, because as mentioned, this is an ISM band, industrial, scientific, and medical. So a lot of commercial devices use it, as well as a lot of rocketry teams use it because you don't always need a special license for it. There are many transmitters that don't require a special license. So here we can see the actual data comparing the reflector to without the reflector. The top graph here, without the reflector plate, shows that we actually have a pretty significant downward facing load. That means the antenna would unfortunately be able to pick up a lot of signals below it. If I walked past it with my phone, that could interfere with those signals. However, once we added the reflector plate here, it actually reduces that load down so far that it's actually off the grid. It's much, much smaller. For reference, the green and red lines represent the azimuth with the best and worst gain, respectively. This is just so you can see, essentially these bound the range of possible gains, and it's a lot cleaner to see than if I had plotted them all at a high fidelity. And it matches up with the characteristics that we defined at the beginning of the receiver section, which is, as you can see here, it doesn't drop below 0 until 60 degrees above the horizon, even in the worst case, as well as it's positive all the way down to the horizon, even in the worst case. And in fact, for much of it, it's up to 2.5 decibels of gain. Our goal was to have positive gain over the entire area of interest. This is not strictly required, but it enhances our link budget as much as possible, meaning that interference, weather conditions, anything will be much less likely to cause us to lose our link to the rocket. And as mentioned, the addition of the reflector plate, which was one of our main engineering projects throughout the year, demonstrates a significant enhancement over the original based on the criteria. Any questions?
material of the reflector plate in your antenna?
So the antenna is made of copper tubes with 3D printed caps to protect the inside, and the reflector plate is also a copper plate. We coated it in Flex Seal actually to weatherproof it and prevent as much damage as possible during the transportation and generally route conditions we'll be seeing out in the field.
You know, the reflector plate is rounded coaxial or something?
It is actually.
Or it's just floating.
It's just floating. Yeah, it's a passive reflector.
Okay, it's not.
No.
I noticed in the elevation gain, well, and even just the 3D image of the gain pattern for the receiver, that you went with an omnidirectional antenna.
Yes.
Again, why the omnidirectional antenna for the ground station? A lot of the time we see directional and high gain antennas that you have to aim. What's with the
Yeah, so that's a good question. The main focus of this project actually was to be able to reduce the number of moving parts required. I know a lot of teams here might have had issues with active tracking systems for their rockets in the past. I've heard from a few already in the last couple of days, as well as the fact that having to manually aim for example, a Yagi antenna is a little more difficult than just having something you can set up and forget about, right? We wanted to have it as omnidirectional as possible in azimuth, but not elevation, so that it could be a practical solution for as many applications as possible. This is something you could leave anywhere out on the range, and it would be able to receive data from your rockets. Even if you wanted to leave one out in the field to detect rockets as they're landing, this would be a perfect solution for that, as you don't necessarily know where the rocket's going to land, but this would detect it no matter where it comes down.
And for a lower gain antenna, so it's omnidirectional, but lower gain everywhere that you would get the high gain directional antenna. For our 10K rocket, the distances we're going to be away from the rocket aren't enough to warrant a high gain directional antenna. So a lower gain omnidirectional antenna is just fine.
Yes. Anyone else?
Did you do any real world testing with the system, any range characterization with the system?
Yes, so we did some range testing. We don't have the data here today. Which is too bad. We had a little mix up with the data as we were trying to collect it. But we saw the data coming in, so I guess you'll trust me. Okay, thank you. So we tested it at about 7,500 feet. So being in Worcester, it's kind of difficult to get a long range test, especially
it's in
Massachusetts. You're
That's
central
how it's
Massachusetts. Yeah. So it being in the city, it's also very hilly. It's difficult to find one range line of sight scenario. So we did about a 7,500 foot test. We were transmitting and receiving 7,500 feet apart. And we were actually transmitting. The antennas were on either side of our campus. So we didn't have any line of sight. There were a bunch of trees in the way. The entire WTech campus was in the way. Buildings, a lot of interference in the city. And we were seeing about negative 100 decibels of gain when it was coming in. And for reference, the XP radio modules can receive and distinguish signals down to negative 113 decibels. And the decibel scale being logarithmic, negative 100 to negative 113 is pretty big. So we weren't even going close to capabilities of the radio modules. So based on that test, and given that our tests were pretty much like worst case scenario, which as I talked about before, Spaceport America is pretty much the best case scenario for transmissions. We figured 7,500 feet with the gain we were receiving and the bad conditions makes us pretty confident that we won't have any issues receiving during launch.
And you spun all the antennas around and make sure.
Yes, we did.
Yes. Yeah. One thing that might be helpful is that, and that was with the XP transmitters, right?
Yes.
One way that you could get away with doing range testing out at Stanford, we have a similar problem. We don't have lack of distance, but the noise floor there is so high. And so one thing you can do is when you range test, you attenuate manually the signal and you transmit at a very, very, very low power. And then you can stand from that side of the room to this side of the room and get an approximate range for what the clear air range would be.
Yeah.
Which might be interesting to see the test. You can go back to your campus, dump down the range and see, oh, we could have gone to space with this system.
Right.
Yeah,
Definitely.
You can do that. I have space here next to you, right? The same system.
Yeah, that's a great idea. The XPs have the ability to lower the transmission power, so that would be a great use.
Yeah. So it's already set up there.
Yeah, exactly.
you guys characterize your BW, SWR?
So first we simulated them using MATLAB and ANSYS, and then to validate those simulations, we used the VMA.
Did you do the same thing on the ground station antenna? I saw the graph of the transmitter on the.
Oh yeah. I didn't have it. It was a little more complicated because it has like photographs for the different things, but I believe it was below 1.2 across the band. It was 1.5, 1.2, at least I think.
Did you have to do any tuning for your antenna?
And surprisingly not. It actually came out pretty well. We have the results. It was a little loose, but it was still well within our acceptable parameters.
So when you got like populated your PCB, like you got had it perfect on your
Nearly, we designed when we did the simulations in MATLAB, we designed it to match the impedance as close as possible, and then pop that into a PCB. That way, we didn't have to do as much manual tuning or adding material of any kind.
So I noticed on your dipole blade, it's very wide. It's almost the diameter of the rocket. What's driving the requirement for the antenna to be very, very wide?
The parameters we optimized for were length, width, and the taper angle in here, which the taper angle does a lot of the impedance matching, to follow up on your question. Overall, we found that this was pretty much the optimal fitting within it. I've done some code analysis on it, but I don't remember exactly.
So you want to get it as big as you could while it still fits inside the.
Essentially, because 900 megahertz is about 32 centimeters. So we can't get a full 32 centimeters in here. We just don't have the space in the rocket, but we want to get as close as possible so that we would have to minimize that impedance matching required.
How many layers?
How many layers is the board? I believe it's just the one layer at the top.
How future work are you kind of doing this?
So future work for this, we would like to be able to do some of those more complex simulations I mentioned, being able to optimize the actual pattern of the transmitter antenna a little more. That's something I've been working on actually in some of my spare time, so that we can potentially, if it comes up, move away from the blade dipole, which, as mentioned, tends to be pretty large, as well as further optimizing the patterns of both antennas.
Having both these antennas hopefully work during flight will give us the room to experiment, knowing that we have a system that already works.
We do have a number of things that we're interested in looking into, but like Will said, this will be a perfectly functional backup that'll work in pretty much any scenario that'll work. Sorry. All right, thank you guys. I get one.
Goodbye, Arjun.
That would stay in model. Yeah, it's going to long. And no, I was 45.
Yeah.
Okay, if you go to wait, now. Oh, it's mandatory exit.
No, I didn't.
See, there's if I make it, yeah. And Judge. So at the end of the competition, like, you are able to reach out to your judge and ask credit. Feedback. We don't get any of the judgment. Yeah, so many things. Can't send you the limit. We'll just give you like you'll see your score, of course, and we can tell you where you can get. Okay, all right, cool. Thanks.
We got one team coming late, and this one just recorded.
Good thing I just shut the stream down.
You did it?
I didn't.
Okay. Thank you. Brett? You're too good?
Yes.
Okay.
There's
Yeah.
They did a very good job.
I'm the flyer of record for that.
Okay, great. Yeah.
Yeah. The guys from Barcelona.
Yeah. Great.
Yeah. I love that one.
Yeah.
So that's a good example. All right.
These two. Good. Yeah.
You know, it's just
Yeah, like even.
Yeah, absolutely.
Yeah.
What will you two running?
Well, him presenting, I think there are 2 or 3 more people around the time. They should be able to discuss this.
Send me.
Yeah.
And then I could maybe add some notes.
Do you understand your method?
Yeah, if not, we can also. I'm not sure. Not your name. But you so when we get to administrator with have a nice cat.
Okay. All right. Well, whatever is easiest for you.
She what was my question? Like you want to
circles?
Yeah.
Marco? There you go. Yeah. Brett, are you the second judge? Then you're gonna go. You're the third one. Once we're done judging yourselves, put them collectively onto one sheet per needle.
Okay.
Thank you.
Yeah, do tell me what.
See.
We were there.
I hope it was more.
Food, where you got up?
Who is the parties for us?
Anyone else?
No,
Thank you. One.
Thank you.
Wonderful.
Okay. Thank you guys for being here, first of all. For Project West, we've been speaking about this a lot previously, but here we are trying to show you the advanced capabilities of our simulation software that we developed named Whisper. So, first of all, I'm going to provide a small introduction to West, which is for most of the people here not necessary because we already went over this. But I also need to do an introduction to Whisper, why we even designed it, what the limitations of OpenRocket are, and what the current capabilities of this software is. We're going to talk about the future developments at the very end and how we're going to integrate with one of our systems. So first of all, VAR-Rocketry West is part of VAR-Rocketry, a bigger association which has over 150 student members which are active. WESP itself has more than 40 students that are active throughout the whole year. It was founded in May 2023 and it has seen a rapid development. We had several launches as part of our rocketry. EX3 was part of Project Cryosphere. Project Cryosphere was a hybrid propellant rocket that launched at FAR. They went to over 14 kilometers, which is approximately 10 miles, a bit less. And they launched last year. They had a hybrid system that had over 2,000 pounds of force. And then Project West launched very recently on the 21st of April. We had EX1D, which was our single stage maiden flight. That was successful. We did a recovery stress test for that. And we're presenting EX1E, which is our second two-stage rocket that we're launching to Spaceport America with a target of 30,000.
So about our initial maiden flights, our apogee was of approximately 440 feet. You can see a video of the actual flight. What we wanted to test out is how the recovery system behaves under a lot of stress at the maximum velocity it could get. For that reason, it was deployed right after burnout. It was really exciting to see that the two parachutes survived and they withstanded over 60 feet per second, 60 meters per second, which is approximately 180 feet per second, more or less. And that just makes us sure that SAC is going to be a recovery success for bottom recovery. As for EX-1E, it's a two-stage rocket. You've seen it. It's a chunky boy. We have a lot of innovation in it, and we're carrying some payload that is developed by our sister project, Space Labs. They have experience with other ISS experiments, and some of the innovations that we are presenting is our ESRA hydrocarbon airframe, the light telemetry that we can actually see during the real flight. Also, our radio frequency that we're using of 2.4 gigahertz of LoRa, which is an innovative concept for us, but has already flown in other of the projects. Additionally, our motor mount that ensures our engine in space is a hollow titanium additively manufactured piece that is an insane piece of engineering. And finally, Whisper, which is what I'm going to present to you. As for the apogee, we are using Whisper because we are so confident in it that we are trusting the calculations of Whisper in itself more than OpenRocket. Whisper is basically our 6 degrees of freedom dynamic mass simulator for the trajectory calculations. What we have is a tool that can basically simulate all trajectories for the different propellants. There are hybrids, liquids, and solids. We are focusing on solids as part of Project West, but it can be applied to our sister Project Next, for example. We have over 8 active members at any given time, over 14 total developers that have worked on this, and it consists of rapid iterations with version control and people developing in parallel so that everything is optimized and we get the best and the most out of it. Why do we even conceptualize Whisper? We all have a lot of experience with OpenRocket, and we know that there is limitations to it. For example, it is a good case for subsonic single-stage rockets that carries a very user-friendly simulator, but the problem is that it relies on many assumptions. For example, it takes the assumption that you fly with a low angle of attack, which at certain points in model recovery isn't always correct. Additionally, in the calculation of the drag reduction through the boat tail, it doesn't calculate the reduction in drag because of the flow being sucked in after the boat tail, but rather because of the decrease in the area of the boat tail, which is not true. Additionally, for our rocket, we cannot simulate the boat tail within the skin of the lower stage when the two are attached to each other, which means that it's another inaccuracy that we have to account for. And finally, the skins are taken smooth, which is not true because we, for example, have the antennas, we have the fin mounts, and other inaccuracies in the skin. For that reason, we also wanted to make sure that all this is covered and more features, so we developed Whisper. Some of the capabilities, apart from the 6 degrees of freedom simulation, is also adding real flight data to this. This is done through the implementation of interpolation tables, which come from DATCOM. These are corrective factors that we apply to the calculation of our trajectory at any given point in the integration of the calculations. We calculate the safety range. We want to make sure that the uncertainties that were once uncertain with OpenRocket are taken into account with us, like weather conditions that cannot be simulated through OpenRocket because you just input a wind direction or wind speed and you forget about it. And other things that I'm going to talk about later when I discuss these features a bit. Additionally, we wanted to have a graphical user interface so that it's easier for other teams that don't have to do with programming anything. And this resulted in a web app right now. And we can do a post-processing analysis with the telemetry data we obtain from our in-flight computers blue ravens, or any different calls too. As to how we actually produce these 6 degrees of freedom simulations, we thought about using K's equation to calculate the motion of the rocket, but using K's equations, you need to basically model every single particle, internal and external of the rocket, which doesn't make sense for a computationally efficient simulator. For that reason, we took Reynolds transfer theorem, which is basically something that assumes that the flow is stationary, and that allows us to simplify the equations significantly. And one of the, if you can see here, the actual equations that are used for the translation and the rotation of the body are basically taken into account both the rigid body and the dynamic mass of the propellant in itself through the components of the kinematics of how the rigid body behaves, the Coriolis effect, and also the thrust component of the engine. All of these we can go into a lot more detail after if you want to see more in depth, like what we're actually using in the background, but these are the backbone of the equations, which we have to display in a state space representation that will allow us to put it in into the integrator. As to what integrator we're using, we took into account which is a classical methods for integration. We also thought about some variations like 45, which is a bit more flexible and has adaptive step size. It's easily integratable, it is efficient, it's accurate, and it is having increased accuracy. These two graphs are part of our simulator, one of the outputs, as well as the ones before. Any open rocket graph or anything else is displayed and mentioned. But basically, we know that this simulator by itself has inaccuracies because even if you take into account all these equations of motion, you're taking into account the assumption, for example, of a stationary flow. And additionally, we don't take into account the interference between aerodynamic surfaces and the body itself, or something like that, which means that we have to apply corrective factors from real flight data that is spread over 3,000 pages of documentation, which we have access to. So that is being digitalized. We're taking those interpolation tables to calculate coefficients to apply these corrective factors into things like the aerodynamic drag, lift, and normal forces. It is especially useful for supersonic flights because this is where the error accumulates, and this is where OpenRocket and other simulators normally underperform. As we're flying a supersonic rocket, it is especially important to us this use case, and that's with these corrective factors. Some examples of how these interpolation tables look is something like this. The graph on the left and on the right are the interpolation tables for the normal forces. The one in the middle is the coefficient of pressure and how you actually can use these for the different components of the rocket, like the ogive, the afterbody, and the fin. You basically calculate the compressibility coefficient and the slenderness of the part you're really looking into, and you can basically take that value and put it back into your integrator, and it applies real flight data to a theoretical scheme. As to the ease of use, it is of no use for us to have 8 people that know how to use this and the rest of the 150 people that are part of our rocketry to not know what is going on in the background. For that reason, we decided that we have to develop a graphical user interface, which was progressing according to Project West. Through the beginning until the development of the 2-stage, we had the X1D, which made us develop a user interface that was capable of simulating for 1-stage rockets. However, as we moved on to a 2-stage rocket, this was starting to become obsolete, and that's what we pushed for a second major development, which led us to 2.0, which is based in Python and had its limitations. For that reason, we wanted to be able to access these simulations at any point on Earth, having it locally hosted back at Zoom if that was necessary, and if you want to, you can be in Spaceport America, you access the website with the server, you run this through a user interface that is very intuitive, and you can get to actually simulate your results. It's we use a framework called Vue. It is very popular among front-end development, and it has a lot of advantages that we can discuss a bit later. But it is allowing us to integrate with other features like our 3D visualization to around the trajectories. As you can see, this is how you actually kind of input these variables. You can actually create as many stages as you want. It is great because even though more than 3 stages doesn't normally make sense, it has that freedom for the user to use accordingly to their requirements. On the back end is still the 6 degrees of freedom simulation that I've been speaking about. So we could, in theory, also host this in our supercomputer back at home in the LR set, which would speed up how fast and could provide instantaneous results. Sorry about that. Part of Ruby takes very seriously safety. We've seen very hard nonsense, and we've seen very bad opportunities for things to go bad. For that reason, we want to make sure that everything goes according to plan. For that reason, we take every uncertainty into account. Even if we think that we designed our fin can't handle perfectly, there is always certain tolerance that you have to take into account. Even if you think you have the weather exactly to the point, that is not always the case, because that's one of the most chaotic and complex systems there is to model in the world. As you can see, for example, OpenRocket has these graphs, which are a bit annoying because you have to access 3 different graphs to visualize 3 different things without the loss of it being intuitive. But what we did is we took our 3D trajectories, plotted onto our single one. We take these side profiles, the concept of a side profile for OpenRocket, and we create just a single graph that contains everything. Here you've got the wind direction, the velocity, the gusts, the area, the dispersion area over. You can run this for over 10,000 iterations if you want to obtain a Monte Carlo optimization of where you think the apogee and the impact points are going to be. So you can have the launch pad, you see relative to the launch pad where you're going, and you can also see when you have your data after you launch, how far away this was from reality with the impact point. As to how we decided on what weather forecast we use, we took Windy. Windy is very well known, and it is great because it has access to 2 of the most common models for forecasting, which are called GFS and ECMWF. I'm sure everybody knows them. They're the basically equivalent for European and American models. They're the best because they have global coverage. They are governmental projects, so that means that they have a lot of supercomputers behind it doing all the computation, which is very nice because they have a lot of precision. But in the end, we use ECMWF because it has more frequent updates. It has hourly forecasts, and it also has smaller spatial resolution, which means that you can get it more to the point. That's what we're all about. West is about accuracy and safety. So we really needed that. And as an extra, we created a 3D trajectory visualization. So you run your simulator, you obtain the geographical data, which is displayed in the GIS format. It's KML or KMSet, and then you can basically watch the animation of how the rocket launches with your predicted apogee and every condition, orientation, translation, all there is to it. It is compatible with Earth engines, so if you want to, you can also use Google Earth Studio, or you can use our in-house developed JavaScript that does this.
Questions? You're good at done trim as well.
There's still 4 minutes left according to your time start slot.
Since you left, maybe, but since I started talking, because everybody was settling down. As to, because everything has to be very concise and clear, we really need to make sure that the very critical information is displayed in a concise manner. For this reason, we generate automatic reports after we run every trajectory, and we summarize everything into a go, no-go decision table. This decision table is something that we hand in to the person that takes the responsibility for taking the decision to launch, and it basically says, with the competition's requirements and our own requirements, that it is a go or no-go for things like apogee targets, etc. As for post-processing, we also take into account telemetry data. This is an example of our telemetry data back in our launch in Straubing for our single-stage rocket, the X1D. More about that in the Q&A if you want to ask more questions, but we basically use Straubing for hardware and logic tests, which we took this tool to basically use our in-house flight computer to analyze this data. And SAC is also going to be more data validation for our models. For Straubing, for example, you can see that actually what we simulated and what the reality was and what OpenRocket predicted was actually very close because of the limited apogee. Still, we want to take SAC as the next step for Whisper because it is a lot higher apogee. It has supersonic flight, which we didn't have in Straubing, and it just provides more information that we can use. As for future developments,
how many more slides again?
2.
Okay, great. Yeah, because I want to give you the 5 minutes I have for questions.
Yes.
So you can finish your presentation, and then questions will be given afterwards.
Okay. As for future developments, all we want to do right now is validate that the model works, that the DACOM corrective factors are applied correctly, and to integrate it with our sister project, Rocket. Rocket is part of Nexus, and they are basically a design tool for liquid propulsion systems, which is basically what you see has been used to create Cara that you see here, that we showed around. This is Rota, which is the second iteration, and Brunhilde, which is actually right before its hot fire testing back in our facilities in Munich. And how we would integrate this is we put this into the design phase, and everything else is done by Whisper. So thank you very much for your attention. I hope you liked it. Yes.
I have just a kind of a general question. Have you had a chance to do any comparisons like with RAS Arrow or any other simulators to see how accurate your basic velocity acceleration is? Very advanced and not in those packages, but I wasn't clear on how much you've done to validate the basics of the simulation engine for this project.
So basically, we only took OpenRocket because it's the industry standard for model rocketry, and it is very difficult to sometimes, especially with our 2-stage rocket, to simulate the same rocket to give precise enough values so that it is comparable. So the issue is always, are you really testing the same rocket, or are you doing something different and therefore obtaining different results? For that matter, we took OpenRocket as the baseline, and that's what we're comparing our stuff with.
I might have missed it, but how accurate is it compared to OpenRocket?
Okay, so in comparison to OpenRocket
for velocity acceleration.
So with our test flight data, we have our test flight data, we have other rockets, but we want to make sure that this is only done with our rockets to make sure that we can reproduce the data accurately. There is an increase in accuracy of over 50% right now, which is expected to increase further by these application of these corrective factors for supersonic flights, which is especially the place where the error accumulates.
Could you repeat, did you say that OpenRocket is 50% less accurate than yours, or
Yes.
vice versa?
Yes, I said that, yes.
Okay, or subsonic?
For the flight data, which was subsonic, which was limited in apogee to 400, yes.
So you basically have one flight
Yes,
that you
obviously
prepared?
one point is not representative enough to make such a bold statement, because I would have included that in the presentation if we had several flights, as we're going to have after SAC, and we have other projects that are going to use this within our upgrade. But this is what we have until now.
Okay, so you have some work to do to.
Yes.
To continue.
Next steps are all about validation. Exactly.
Milestones. Yeah, we need to record more milestones and probably compare with other sources besides other ones. So you can do your validation and have a more accurate representation for next year. I think is promising.
Yeah, I think it's exciting. I especially like integrating the wind.
Slides. That is the data for tomorrow, which we just use to.
This one, this was taken 3 days ago. The problem is that we've been told that it's very critical if you launch before 12 or not, because there's the wind changes from basically northwest to southeast. So that is just something that we have to assume that we launched before 12, and that's what you were actually seeing here.
What day?
Launch day number 1 tomorrow.
Wednesday, yeah.
10 a.m.
Because windy current, I was just running it
Yes.
as you were speaking.
Yes.
Wednesday and Saturday are the best days.
Exactly.
And before noon is clearly better.
Exactly, and that's what we're trying to do as a project. Launch as soon as possible on Wednesday.
Yeah. No more questions.
No more questions.
Good job.
Good work.
Thank you for letting us read the movie. You're welcome. You're good to go? Good evening, guys.
Yeah.
Yeah.
I really like
I'm curious to tell.
So,
So did you already?
So,
Yes,
we're gonna do that
told me yesterday.
tomorrow. See you guys tomorrow.
yeah. Reasons we always
Yeah. So they wrote me. Actually, had a second. I had a second. No, but they they have a Tuesday, great. Or meanwhile, I'm more of a Tuesday.
Then you're in the third.
You're gonna and what's the last day? Now the beach hunter.
Yeah.
Good work. Tomorrow or
no, we're doing tomorrow.
Yeah,
Yes, it's
Really hard.
See you tomorrow.
Because we talked.
And yeah,
I don't
we'll talk much more about this. I like the innovation. There's
We're trying to make it as soon as possible. Just a little bit of time.
Yeah. Okay. Thank you for taking your time. No worries. Yeah, it was a pleasure.
Yeah,
So
yeah, I'm with you.
Yeah. So where I was going.
That's one of my portfolio clubs, let's say it like that. And you know, I'm flying rockets since 2007.
For a long time now.
Yeah. I also started small, you know. Yeah. And 18 it was time. So even Poland, we were flying from Poland.
Okay.
I don't know if you know about the scene in Poland.
Not really. No, we had some conversations with theory delegation on Spaceport, but not really. Or
Yeah, in Poland, there was there's a good local organization that will organize for students from Poland stuff, and it was so nice because
Thank you.
it's like
No problem.
almost no paperwork, military base.
yeah, I know it
They
is.
close